I found this wonderful relationship between fractions and tangles. Tangle is a word I use for a piece of knottedness that has some ends coming out. And some tangles are fractions. So, 2/3 for me names a particular arrangement of string. And this was taking, how can I say it? Knot theory is a branch of topology and so on. And then here's this little piece of it that's the same as arithmetic, elementary arithmetic. That's really what I love. I'm interested in rather trivial things, frivolous, unimportant, games, working out the day of the week. And I had to sort of struggle to get the license to be interested in trivial things.
Do you feel you missed the chance to explain the monster by leaving Cambridge? There was a lot of momentum built up on the group.
Yes, I don't know. I mean, the way I think of it is there's a geometrical object, like the kind of star you might hang on your Christmas tree, which is tremendously symmetrical. And however, it's very, very big. An icosahedron, one of the regular solids, has 12 vertices. A dodecahedron has 20. And they have 120 symmetries. You can view them from 120 different positions, and they look the same. Well, the monster, it has nearly 10 to the 54 symmetries, a huge number. And where does it live? Well, the geometrical object that supports it is in 196,883 or 4 dimensions. You can't really think of this monster, and yet somehow, collectively, we mathematicians did, And I don't understand why it's there, and I really want to.
I've always meant to ask you about the discovery of your group because, I know you primarily as a group theorist, and I think it's an interesting story.
It was in Moscow that I first learned things. At the International Congress in 1966, I met my strange friend John Mackay, who you know. Perhaps I should call him our strange friend. Hope he won't mind being called a strange friend. I was leaning against a pillar eating some bread and salami or something, some thing that they sold just in the basement of Moscow University during the Congress. And this man approached me and said, "Are you Conway?" And I said, "Yes,
So he wasn't your friend at the time?
No, he wasn't. He told me about this wonderful sphere packing discovered by John Leach, which is packing of 24-dimensional spheres. And he thought it had an interesting group. I'm not quite sure whether it was just Leach who thought or whether Mackay thought on his own account. I looked at it when I got back home to Cambridge, and I thought, yes, this must be. It seemed to be very, very symmetrical. Group theory is the study of symmetry. And it looked very symmetrical to me, this wonderful sphere packing. And so I approached John Thompson, who was the best group theorist in the world, and I think still is, and told him about it, and sort of suggested he should look at this. And then, after a few weeks, he never seemed to have looked at it. And I eventually said, "John, you're not going to look at this, are you?" And he admitted as much. And apparently, at that time, these interesting, simple groups were all the rage in mathematics.
But there were very few of them. At
Yeah,
that
there were
time.
very few of them. What had happened was Mathieu discovered some in 1861, and then a century went by until 1963, I think it was, when Yanko discovered another one. And that sort of set the group theoretical world thinking about these things. Thomson sort of said, if you find the order of this group, that's to say the exact number of symmetries it contains, then I'll be interested. Until then, I'm not. And I told my wife that if this thing works, which of course I didn't know, it's going to be rather big and it will make my mathematical name. And so she was very understanding. But I was doing an enormous amount of teaching at the time because I didn't have a proper job. And we worked out that I could afford to spend 6 hours on Wednesdays from 6 p.m. till midnight and 12 hours on Saturdays from noon till midnight. And anyway, it came to the first Saturday. I wish I could remember the exact date. Maybe.
But it was some years after Moscow, I think.
Yeah, it was. It
68.
was 1969, I think. Maybe 68. Anyway, I sort of kissed the girls goodbye and went into our front room, and they were told not to interrupt Daddy. They didn't understand why. Whatever. Daddy just seemed to be scribbling on paper, but they didn't sort of think it was important or anything. But anyway, they promised not to go and interrupt Daddy. And then Daddy went in, and, you know, we had just moved into the house we owned, and the previous owner had left a lot of equipment behind. He made his living by moving into houses, which were sort of derelict to some extent, and doing them up and selling them for much more than he moved into them. So he sort of typically lived in a house for about a year, I suppose. Anyway, he'd left huge rolls of wallpaper backing paper, great rolls of white paper. So I put one of them across a table and I started writing. And as I continued to discover a little bit more about this, you know, I just pulled it down and so on. And I wrote about 6 or 7 feet in the end. And then at about 6 o'clock, I worked out this magic number that John Thomson had said would make him interested, you know. And I telephoned him and said, the number, well, I didn't actually know it exactly. I knew it was either a certain number or twice that number. So I told him what I knew. And then he was as good as his word. In about 20 minutes, he telephoned back, and he was very, very excited. He said, you know, any group of this size with these properties, you know, he knew something about it. Oh, by the way, he said the order is one particular one of these 2 numbers, and it involves the McLaughlin group and the Suzuki group and the Higman-Sims group, various other things that had just been discovered, essentially.
And the whole Yanko group.
I don't know whether he had the whole Yanko group in there, but he probably did. He was as true as his word. He was very excited and interested. And we kept on telephoning. At about 9 or 9:30, I had discovered a way in which I could prove that this group existed. There was a certain calculation, and, you know, I could see that I could do this, and if it existed, which was obvious to me that it did at the time, I could prove it. And I said, but I'm absolutely exhausted, so I'm going to bed now. And then, after putting the phone down, I thought a little bit. This repeated itself several times. I thought, oh, I'll just do something, you know. And so at 10-something, I telephoned him again, and I said, you know, I've worked out a way of finding an element and so on. Anyway, I kept on like that. And finally, I had about 5 calls, in each of which I said, I've reduced it to a certain problem, but I'll tackle that tomorrow. But in every case, I sort of thought, oh, maybe I can just, with this extra idea, maybe I can just do it. And so eventually, at 12:20, I telephoned him and said, I've done it. That was a Saturday, and we arranged to meet next Sunday morning, and it was cold and damp in the department and so on. And we just started working together. And we didn't stop. Thomson, at that time, was spending 6 months in Chicago and 6 months in Cambridge, but he actually spent 18 months in Cambridge, I think it was, because he didn't want to stop working on this group. And it changed my life, utterly. I remember meeting the master of my college in Cambridge, and he just knew that I'd made some breakthrough. He was a historian. He didn't know what it was. And he said, oh, I haven't seen you for some time. And I said, well, I've been in Göttingen last Tuesday. These dates aren't exact, And and then I was in Paris, and at the weekend I fly to New York and so on. It turned me into a jet setter. It was fantastically exhilarating. And from being known to nobody, I suddenly became, one of the mathematical names known to everybody, essentially. It's hard for me to think myself back. Before then, I was in a sort of black period, I always think of it, or maybe blank period. Nothing seemed to work for me. I had published one little book on a totally different subject, but it wasn't all that interesting, and everybody's forgotten about it. Oh, they haven't.
They haven't. I tried to get it this year. It's for sale for $800 online.
$800, yes.
I don't know if you've got any spare copies.
Actually, Dover, this publishing firm, is going to reprint that book. At least I think
this is for regular algebras.
Regular Algebra and Finite Machines, it was called. It was an idea of this logician, Kleene, who wondered about an orgasm, my God, there's a Freudian slip for you, an organism. How it could be modeled. He's really thinking of a finite machine.
Was this the beginning of finite state automata?
Yes, I think so. It was a very interesting book called Automata Studies that he wrote this paper in. And he wondered how to capture the fact, how an organism, a mechanical organism he's really thinking of, could interact with its environment. The environment presses various buttons, inputs to the organism, and the organism responds by lighting various lights, basically. In other words, it's got input and output devices. And Kleene found an interesting algebraic way of studying these things, and I got interested in that and wrote my first book. And then you know what happened? I got 2 copies of it from the publishers, who, by the way, are the Chapman and Hall, who were Dickens's publishers. And then I walked into my college and I met my old applied mathematics teacher, and I said, look, meaning I've published a book, He
took it.
And he said the worst thing he could possibly have said, he said, thank you. So after that, I only had 1 copy. And then I lost that copy. And then I stole another one later, but I don't suppose I should confess that in public.
Getting back to your group, I suppose in those days the Leech lattice was not so straightforward as it is now. I mean, now it doesn't sound that difficult to find the order of the automorphism group.
Anything that I get interested in, my job, I think, is to simplify it, and make it easy. And so I have a sort of baby treatment of anything. So, I always think if I can understand it, I can help anybody else to understand it, probably. I find it very hard to understand things. I mean, most mathematical lectures, as you know, you go along to them and you don't understand a thing, 5 minutes at the front, and maybe there's a finishing thing. And I think that's absolutely ridiculous. So whenever I talk to people, I try and make everything terribly, terribly easy. I make a living by not understanding things, in a sense. I'm good at not understanding. And then eventually I succeed in partly understanding something, and then I think anybody else can, So I really think of myself, I do think of myself as a mathematician, but as a teacher, I really like teaching. Maybe we should talk about the life game. I met Martin Gardner a long time ago. He just died last year. And I used to go and see him a fair amount. And one time I told him about this life game, which was quite astonishing. And this was a recreation that we played in the common room of the math department in Cambridge. And it had very simple rules, and it behaved unpredictably. What happens is you have little objects, you model the world by plane ruled into squares, and you throw some counters down, more or less at random, and then it just evolves. If there are 3 counters next to a given one, it's rather peculiar. You have 3 parents in this game, and if there are exactly 3 counters next to a given one, something is born there next time. But it only survives if there are exactly 2 or 3 counters. This game became tremendously popular. In fact, Martin told me, this is Martin Gardner I'm referring to, that Scientific American got more mail about it than about any previous article, except the first one he wrote. And the first one got more mail about it than any previous article in Scientific American. And it was about hexaflexagons. Actually, Richard Guy, who's a friend of mine, who's now 94, he wrote a little article about me once, and he said John Conway is celebrated, celebrated for discovering life at Cambridge, he said, which was some kind of backhanded comment about my colleagues, I suppose. But anyway, this game called Life is played on an infinite board ruled into squares. I might as well add this one here. And you start off, each square is called alive, in which case I'm writing an X in it, or dead, which is, I leave it blank. And actually, I can write something other than the X if it's alive. And to survive, a thing needs to have 2 or 3 neighbors. It needs to be alive.
So these 2 on the edges will die off?
Those creatures will die off. So let's just put a little sort of circle around them to indicate that they're getting old. They're going to die soon. But this one has 3 neighbors. The neighbors of the square in the middle are the 8 squares around it. So this one has 3 neighbors that are alive, it's time 0, by the way.
Corner one has 2.
This corner one has 2, so that's okay. This has 3. This has 3. Oh, but okay, so those 3 survive. And then the conditions for birth are that you be in an empty square that has exactly 3. For birth, it's exactly 3. So this thing here, there's going to be a happy event in this square in a moment. And there's another one here. Okay? And if you think about it, those are the only squares that are not live at the moment, but will be next time. So what we do is we rub out these, because they're dead now, and we elevate these dots to crosses, and there we are. The time is now 1. And then we do it again. So what happens is this one has 4 neighbours, 1, 2, 3, 4, so it'll die. This one has 1 neighbour, so it dies. This one dies of overcrowding in the middle. This one dies of isolation, even though they're right next to each other. Nothing else dies.
And this
But
one.
there's something going to be born there
And up.
and something there. Hope I've got that right. So now we rub out these poor corpses and we elevate these to crosses, and the time is 2. It turns out, well, let me just show you where we'll be at time 6. Let's just remember that this is where we are at time 2. I'm just redrawing it. And I'm going to emphasize this portion. And then I'm going to delete it all and insert rather, where we'll be at time 6, and it is here. This is where we are at time 6. And that's exactly the same shape as we were at time 2, but it's moved down 1. Okay. So this little beastie will sort of walk across the plane. And I've always regretted the name I gave it. It's a glider. And that was called not because it glides, but because it moves by glide reflection. But let's not worry about that. If you actually see them on a computer screen going at a reasonably slow speed, they look like ants, and I wish I'd called it the ant. I mention this because it's what convinced us that life was interesting. Now, what do I mean by us, and what do I mean by interesting? By us, well, I'm one of us, and there was a floating collection of graduate students, and we used to tinker with these ideas every coffee time or tea time. And we did this for about 18 months, every now and then trying a new rule. And we were never quite happy with the effects of the rule, but eventually we were. And I still remember the day on which we found this object, the glider, because my friend Richard Guy, who's around, active at age 94, he had been given the job of looking after the small configurations that weren't near the majority action, so to speak. And he said, come over here, my bit's walking. And so we came over there. His bit had fallen off the table. We used to play this on go boards, on
Counters.
coffee room tables. And every now and then something stretched beyond the confines of the table. So we came over there and looked at his bit, and it was this thing, and it was indeed walking. And that excited us very much because we finalized on this set of rules. We knew something interesting was happening here. And eventually we proved that this life game can do an arbitrary computation too. It's quite astonishing. You can set up a finite configuration and ask it to look for solutions of things. I mean, what used to be the standard example was Fermat's last theorem. Do there exist two perfect nth powers that add up to a larger one?
So you just set up the
Yes, well,
configuration.
you could, in principle, set up a kind of computer, but it's not a real computer. It's a thing made out of a life configuration, and set it searching for triples of numbers, quadruples of numbers, a, b, c, and n, such as a to the n plus b to the n equals c to the n, and n is at least 3, and a and b are less than c, and so on.
And your life game would unfortunately go on forever.
Well, yes. I mean, it would go on forever unless there's a solution to Fermat's last theorem, and it would stop. And we proved that any mathematical question of a sufficient degree of precision could be phrased as, does this life configuration last indefinitely or not? And you could devise a particular life configuration to do it. So that's captured in the phrase, life is universal. That was another really exciting period of my life, the life period of my life, so to speak. For a long time, I was defined by the life game. It was started by something else. Oh yes, a paper of von Neumann's. Oh my God, why did I forget von Neumann? Von Neumann was a fantastic mathematician, and he had a sort of foray into biology. I was rather surprised. Fairly recently, I attended a conference which was mostly addressed by biologists, and they all regarded von Neumann as, they were sort of mathematical biologists. They regarded von Neumann as their sort of progenitor. He was a very interesting guy. And anyway, somehow I've kept on coming back to various things of von Neumann's. And we've intersected a lot. I think it's a sign that von Neumann was interested in so much, you know. I wasn't interested in making bombs, which were one of his claims to fame, but I was interested in all sorts of mathematical topics that he started off or continued in various ways. And yeah, I'm now the von Neumann Professor of Mathematics at Princeton. I only get to use that normally when writing references for students. I sign it at the end, you know, John von Neumann, Distinguished Professor of Mathematics or something. And I can pretend I'm doing it for the students' sake.
But it gets you an invitation to all the von Neumann meetings.
Yeah, I get invitations to conferences about von Neumann, which happen every now and then. There was one occasion when the Hungarian Academy of Sciences, on the occasion of the 100th anniversary of his birth, commissioned also, well, they had all sorts of events. There was a von Neumann year. And in Princeton, they found the place where von Neumann's first computer was operating, the first computer, perhaps I should make it perfectly clear, which was now in the nursery school of the Institute for Advanced Study. And they put a plaque on here with von Neumann's head on it in relief and so on. And it was rather funny. We went there, the mayor of Princeton was there, a lady called Phyllis Marchand, and my friend Simon Koshin and I, we went, and I remember it started raining just before the appointed time for this plaque to be revealed to the world. And we stepped into the Institute Nursery School, and there were little kiddies on tricycles running around between our feet, and all these distinguished Hungarians and so on. And then we paid a visit to von Neumann's grave.
And this was the occasion where we opened the box.
Oh, the box. That was, that's a fascinating thing, yes. I'd met von Neumann's daughter a number of times, Marina von Neumann, who became an executive at General Motors and was a very distinguished lady. Anyway, at one time, at one of these von Neumann meetings, we had lunch together, and the topic of conversation was the box. Von Neumann had left a box with some papers in it, not to be opened until 50 years after he died. And Marina's daughter had been saying, "Come on, Mum, let's open the box. We don't have to tell anyone." Marina said, "No, Daddy wouldn't have wanted us to open the box before he said, you know." And then they opened the box eventually, and it was nothing to do with von Neumann. Von Neumann's wife had married another person, and it was her previous husband's letters that were in the box. And it was nothing interesting at all.
You've also been interested in other devices that perform computation, as well as the game of life. I think you've got a computer language.
Yeah, it's a rather strange computer language. I called it Fractran, making fun of Fortran.
And in fact, its goals are probably the opposite of goals of Fortran.
Yes, I have a particular Fractran program called Prime Game, and it's a list of 14 fractions, and you start with the number 2 and repeatedly multiply by the first fraction on the list that you can, that gives you an integer.
So that's the program, basically, or
That's
that's
the
the
program.
operating system.
It's
perhaps, of the
really a
machine.
computer program, but written in Fractran, which is a language like no other. You start with 2, and you keep on multiplying it by the first fraction you can, and then you watch for the powers of 2. That's what you're told to do. And you find out that they're 2 squared, 2 to the 3, 2 to the 5, 2 to the 7. I wonder how many people guess the rule from that. 2 to the 11, 2 to the 13. The answer is you get 2 to the n if and only if n is prime. And so it's effectively a computer program for computing primes. And it's astonishingly simple. Trouble is, it takes a long time. To compute the nth prime takes roughly n cubed operations. So to compute the 100th prime, will take 1 million operations. To compute the 1,000,000th prime will take 10 to the 18 operations or something, which is absolutely huge. And so it won't get anywhere in your lifetime, so to speak. It can also compute, if you do a different list of fractions, it can compute anything you like that's actually computable. And in particular, I wrote a program that computed digits of pi with 40 fractions instead of 14. That is so inefficient to get the first digit after the decimal point. Well, you'd have to wait until the universe grows cold.
To get the 1.
To get the 1, yes. 3.1415, etc.
But nonetheless, the programs are very short.
Yes, you see, what those programs emphasized was shortness of program rather than shortness of the time taken to compute something. I was really concerned with theoretical computation, not practical computation. I'm a very impractical person.
Well, not necessarily. A lot of things you've done have been efficient algorithms for calculating with groups, for instance.
Yes, I'm not terribly interested in the algorithmic side,
But you are interested in doing the calculation efficiently and cleanly.
yeah, that's true, and elegantly when it can be computed elegantly. You know, I'm a great admirer of Coxeter, famous geometer, and I absolutely love his work, and very, very elegant geometry.
Well, let's go back long before Cambridge. When did you first realize that you were a mathematician at heart?
I don't know when I first realized. My mother said that she found me reciting the powers of two at the age of 4. Now, she was a fond mother, and I don't know exactly what was meant by that. It might have been 1, 2, 4, 8, or maybe I got up to 1024, 2048, and so on. But anyway, that's a sign of something. When I went to, you know, at that time we changed school in England at the age of 11, or 11 plus it was always called. And when I went there, I had an interview with the headmaster.
At the high school?
At the high school, yes.
Which high school was it?
It was the Holt High School in Liverpool. And the headmaster sort of said, what would I like to do with my life? And I said, I want to go to Cambridge and read mathematics. I heard that phrase, read mathematics. It seemed a grown-up phrase, you know, so I sort of used it.
And what did he said? That's impossible? Or?
Yeah, I don't know. But anyway, what happened, though, is I wasn't particularly mathematical in the first few years at that school. I was sort of roughly good at everything, but particularly the scientific things. And I remember in my first year there, I came first, second, or third in every subject, you know, at the end of that. And then several things happened. I became more restricted to mathematics as I get older. Also, puberty happened, and I sort of got less interested in school at the same time. And then I remember one of the teachers having a talk with me and saying, you know, you're wasting your life. This was at the age of 15 or 16 or something. And you really should knuckle down and so on. And I took it to heart and eventually got into Cambridge, which was what I had told the headmaster I wanted to do at the age of 11. At the age of 11, of course, I couldn't see further than the age of 18 or whatever it was. But it sort of seems as though I was always a mathematician in some sense.
And I think that some of the things you started investigating in high school have turned into long-term projects and become quite important, haven't they?
Yeah, the one I particularly think of is my interest in knots. I read some popular book on mathematics, and it had a picture of a knot in it, and it said the simplest algebraic description of this knot is, and then there was some complicated formula, which I didn't understand. But it started me off being interested in knots, and I kept up that interest when I was an undergraduate at Cambridge. And I remember I used to go down to the Central Reference Library in Liverpool, and I picked up some 19th century papers on knots and got very interested. And then discovered a whole lot of things about them. You know, when I got to Cambridge, I started off by making a sort of dictionary of knots. Then when I got to Cambridge, I realized that just enumerating knots was not a terribly mathematical thing to do, you know, and it would be more grown up to work out invariance. And so I worked out some invariants of knots, I tabulated them, and then discovered some properties of them and so on.
30 years ago, you said this strange thing. You said the real invariant of a knot is a knot itself and there's nothing else. But sometime after that, your invariance became useful and
Yes.
pushed a long way.
Well, it was not really my invariance, but my sort of method of computing invariance. I found these relations between, if you take a knot and just change one crossing of it, you just pass the string through it and so on. There are relations between the invariance before and after, for some of the invariants anyway. And I started thinking of knots like that.
So you gradually simplify the knot and
Yeah.
watch what happens to the invariant.
And then I found, I think this was when I was still at high school in Liverpool, but certainly by the time I became an undergraduate in Cambridge, I found this wonderful relationship between fractions and tangles. Tangle is a word I use for a piece of knottedness that has some ends coming out. And some tangles are fractions. So, you know, 2/3 for me names a particular arrangement of string. And this was taking, you know, how can I say it? Knot theory is a branch of topology and so on. And then here's this little piece of it that's the same as arithmetic, elementary arithmetic. That's really what I love, you know, when you have some unseen connection.
And if you know the complicated fraction for the knot or for the tangle, you have instructions to untangle it.
Yeah. Oh, yeah. Well, I think you're referring to what...
one of your famous lectures.
Yeah, on one of these lectures, yes. I have people square dancing, holding ropes, and they get the ropes into a terrible tangle. And then I sort of instruct them. Well, I cover up the tangle with a plastic bag usually, so nobody can see it anymore. And then I instruct them to untie it. The audience has to untie it by telling the dancers what to do. And, you know, if they get it right, which occasionally they don't.
But at Princeton, it's usually okay.
This terribly tangled thing messes the plastic bag up. I go up there and pull it away, you know, bite the plastic bag, and whoosh, the tangle. Well, when it works, the tangle comes undone.
Who were the influential teachers you had as an undergraduate in Cambridge? Who did you like learning from?
It was influential and interesting. The most interesting teacher, I suppose he was influential, was Abram Samuelovich Besikovich, a Russian emigre. The students gave the talks, and Besikovich sat in the audience and sort of acted as a compere and so on, and maybe suggested topics. And this was attended by, I don't know, 6 to 10 students, you know, the bright ones, roughly speaking. And I got to know Besikovich reasonably well. He was notorious as a lecturer. Unlike the other lecturers who would sort of drone on a bit, he would every now and then stop and say, "You! What was I going to say next?" And the person would quiver a bit and say something, you know, I don't know what he would say. "You think I'm a fool? Why should I say such a stupid thing?" And so on. But Besikovich was really very kind. But his lectures were absolutely fabulous, and I enjoyed them very much. Although I may say they were on Lebesgue measure theory. I didn't really have much interest in that subject. I do remember one occasion when he said, next week we're going to discuss a very, very important theorem. And so the lectures were on Monday, Wednesday, and Friday, let's say. And on Monday, he came in and he proved this theorem after telling us again how important it was and how we should take notice and so on. And so fine. And then he said, on Wednesday, we will have applications. So we came in on Wednesday and we had an application. And my God, the theorem said something that didn't seem to be true. You know, he got some kind of contradiction. He said, you! What is wrong? You know. And whoever it is said,
The theorem's false.
that function isn't continuous, you know. Did I say it had to be continuous? You will all look at your notes, you know. Did I say it? No, he hadn't said it had to be continuous. You, what is wrong? So another thing. Well, I was the person who in the end said what was wrong. I said, perhaps what is wrong is the theorem. And he said, yes, you are right or something. But this discussion had taken all of Wednesday's lecture. And he said, on Friday, we will prove the theorem again. And this time, you will listen. And so on Friday, we came and he proved the theorem. And then I can't remember whether I pointed out what was where the mistake was or somebody else did. I honestly don't know.
Friday was the same proof as Monday.
He started off in the same way, but then, you know, when somebody pointed out that there was something wrong, he clarified it and so on. He tried to go wrong several times, you know, just to fool us. It certainly made us listen, I must say. And I thought it was quite amazing. And I tried to do the same thing in my own lectures a little bit. So in a way he influenced me, not so much as a mathematician, but as a teacher. But I never had the personality to carry it off.
Well, really, you have done with a Lexicode talk.
Yes, in a way, but that's, you know, not really part of routine teaching. Besikovich had this tremendous personality, and you know, he could really carry it off, and he never seemed to worry about where he was, you know. By the way, he had grown up, he'd been to university in Siberia, and it was so cold that they kept sacks, burlap sacks, in the lecture room, a great heap of them. And the students, as they came in, encased themselves in these sacks and sat there. So Besikovich was used to the cold. So after a time, he would strip off, he would take off his jacket, and after a time he would say, the young ladies will not mind. I don't know whether the young ladies minded or not. And he would take off his sweater and so on. And he always ended up with his braces, suspenders, you know, over just his shirt. And then he would insist on having the windows opened. And the lecture room was freezing.
Because Cambridge is quite a cold place by English standards.
So he was quite noticeable. He also had a card game, which I played with you. This card game became quite well known. It was said that there were only two people who had ever beaten him at this game in the West. It was a Russian card game.
But he'd adopted the rules, I think it was.
Yeah, he changed the rules a little bit. The two people who had beaten him were Hardy, who was the Rouse Bowl Professor of Mathematics before Besikovich, and Littlewood, who was the Rouse Bowl Professor of Mathematics after Besikovich. I should have mentioned that Besikovich was the Rouse Bowl Professor of Mathematics, of course. And certainly we used to go around to his rooms in Trinity College, you know, 4 or 5 undergraduates and play him at this game, he would do a sort of simultaneous display, you know. He'd walk around tables and make his moves. And we never beat him. And then he retired and spent a few years in America going around giving lectures in places, and then came back to Cambridge. And I met him at the house of this Russian lady mathematician who used to sort of give parties for the Russian community in Cambridge. And I played him at this game, and my God, I beat him. And however, I wish I hadn't. He was so upset. And I only beat him, I think, because he was getting old and he didn't pay attention.
And the game is a bit unforgiving. If you make one mistake, you're in big trouble.
Yeah. Yes, it's a frightening game in a way. It has the most negative feedback of essentially any game, you know. In other words, it's not a question of making a good move. All moves are bad for you, and you just choose the least bad one. It's a very intriguing game. I got interested in games, and I mean really children's games, usually played with pencil and paper or something, but really very childish. One of, dots and boxes.
Is this also from high school? Or?
Yeah, I mean, I'm not sure how interested I was at high school, but I read this paper by Richard Guy and Cedric Smith, which sort of told me about this theory, and the theory was by Grundy and Smith, P.M. Grundy. And it was about adding games up. And they only considered games in which the moves are the same for the two players. And you might think that chess is like that, but it's not. In chess, one player moves the white pieces and the other player moves the black pieces. And although the moves are similar, they're not exactly the same. It's illegal for the black player to move a white piece and so on. So games satisfying that condition, that are called impartial games, are very special and rather unlikely. And I always intended to try and generalize this theory of Grundy to what I call partisan games, where the two moves are different. And then eventually, I did nothing about it for a long time. And then eventually we had the British Go champion in our math department in Cambridge. And he used occasionally to play Go against some of his friends, in the common room in the department. And I used to watch and try and understand why this move was better than that one and so on. I never understood anything about Go. But I did, I suppose I understood one thing, which is that at the end of the game, it sort of breaks into a sum of games. And I decided to study sums of games. And my God, that was another thing that was quite astonishing. I discovered that some games behave like numbers.
This was in the period after the Conway Group?
Yes, it was.
Probably immediately after.
I can't remember. Everything gets jumbled up in time. There was a notion sometimes of a player being one move ahead or something, and then you could be 2 moves ahead or 3 moves ahead and so on. And it's perhaps not a good idea to call it moves ahead. The value of the game could be 1 or 2 or 3 or -1 if it was for the other player. But then after a time, I found that there was a concept of a half. There was a game, 2 copies of which added up to precisely 1 move. 1 move, by the way, it's a game. Namely, it's a game in which the player left can make 1 move, and the player right can never move at all, and it's not a very interesting game. You have a starting position, then from the starting position, right can't move, but left can move.
So right is
And
lost.
if left moves, it ends the game. And you wouldn't think that's a very interesting game, but you can add it to itself, and then you get 2 moves. I often call them 2 free moves and so on. Or you can get -1 move if right's ahead instead of left. And then I discovered you can be fractional numbers of moves ahead. And then after a time, I realized something, which is, rather than thinking of these games as representing numbers of moves and so on, you could think of numbers as games. And so I studied the numbers, and there were other things that weren't numbers that arise in this way, and I discovered there were infinite ones and infinitesimal ones, a whole tremendous world of numbers, new numbers, and they are now called surreal numbers, after Donald Knuth wrote a little book about them. He was the first person to publish them. He was still is, really a theoretical computer person. Yes, he wrote this novel, and in this novel I appear as God, actually, which is...
Yahweh or something. JHWC.
Sorry?
It's JHWC.
JHW, yes. The initials I'm given are the way that Jehovah is referred to in some ways. That book appeared before I wrote anything on numbers. Knuth called them surreal numbers. And I wish I'd invented the name. I should have invented the name. I just call them numbers because I thought that if you needed to have an adjective, you were describing some particular type of number, and this described all numbers, huge array of numbers. In fact, I went around for a time after discovering these things. It's very hard to convey the impression. There were so many of these numbers, and other things as well besides numbers, that there were just huge amounts of unknown territory, absolutely enormous. And I felt, as I imagined Stout Cortez must have felt when he stood on the banks of the Pacific, or something. And monarch of all, he surveyed sort of language as appropriate. I went around in a daydream for a period of 3 or 6 weeks, sort of seeing all these things in my mind, And I must admit that part of the thing was, I said to myself, and you discovered them, John. Nobody else had ever seen them. In a way, I think that's the subject I'm proudest of, the piece of work I've done that I'm proudest of. And it was really play, not work. It was very, very elementary. It followed up work done in the 19th century by Dedekind and people, and a long time ago by Archimedes.
So it generalizes the Dedekind cut.
Yes, and it generalizes the real numbers, That's why they're called surreal numbers. They're above the real numbers. The real numbers are particular cases of them. So, I found a game in which you could say that one player was exactly pi moves ahead of another player, and so on. I think that these numbers are so natural and obviously so right that they should have an application. They haven't really. There was my colleague Martin Kruskal he got very fascinated by the surreal numbers, And he spent about 30 years of his life trying to apply them to what's called asymptotics, but never really succeeded. And I think his project deserves to be resuscitated, but I'm not so keen on it myself. Yeah, the surreal numbers really sent me off into this, I don't know, I must have looked catatonic from the outside. From the inside, I was just dreaming all the time. I was in a new world.
The surreal numbers are just a small subset of
Yeah.
the games.
Yes, you can play games, but you can also theorize about them. And a game is an object, and numbers are particular cases of games. I wrote a book with Elwyn Berlekamp and Richard Guy, which we called Winning Ways, which told you, a lot about games. And we applied this sort of theory to, children's games and so on. And it tells you how to win them. And then I also wrote a book called, this by myself, called On Numbers and Games, which we abbreviated to ONAG. And then I was told that in Hebrew, ONAG means pure pleasure. And so I'm really rather delighted. But then there's also an onaga, or onager, which is a kind of donkey or something, and that rather pleases me. So we talk about readers of this book as onagas. Yeah, I really loved writing that book.
And in the end, did your theory of games have any impact at all on game playing, on Go end games?
Well, not in my hands, but Berlekamp, who was my co-author in the Winning Ways book, he applied it to Go.
And he's quite a keen Go player.
He is a keen Go player, yes. He didn't actually know that I got it from Go in the first place. He applied it to Go. He found, positions in Go near the end of the game where the theory was actually useful. And he wrote a book with a student of his, David Wolf, about Go. And he actually went around in Japan and he was very fond. There was a Japanese professional Go player, and I should say Berlekamp didn't beat him at the game of Go exactly, but Berlekamp set up some rather special position
In which a Go player didn't play optimally.
Yes, in which, Berlekamp could analyze everything about this particular position. And so he met this professional Go player who was astounded that anybody could possibly beat him, particularly a Westerner, shocked, terribly shocked. And he wanted to play the position again and again and again. And then he actually moved, this is the professional Go player, into the hotel that Berlekamp was staying so that he could continue playing him for all the time he was there. And Berlekamp, of course, delights to tell this story. He's interested in Go, and among, American Go players, he's pretty good. Many people, I'm sure, who are viewing this will remember playing dots and boxes at school. It was, in fact, invented in the Polytechnic in Paris shortly after Napoleon set up the Polytechnic School in Paris. Now it's a university, but at that time it was a sort of glorified high school. And the students played it in the way that I think they've played it ever since, you know, on a paper concealed behind the desk while the teacher isn't looking. I remember playing it as a kid. Maybe you do.
I played it in high school too.
Yeah. And we never thought about the game. At least maybe you did. I certainly didn't. We just sort of more or less made moves at random until very near the end of the game. Well, Berlekamp started playing it at the age of 7, and he made a discovery at the age of 7 anyway. And this discovery enabled him to beat all his school friends, you know. And then every now and then, he's made another discovery. And, you know, 60 years has gone by since he was 7. He's probably 70 now. He's kept on making discoveries about this game. You know, I used to play it with my son Oliver a lot, and also with various colleagues at Cambridge. You know, and you see these two people you'd otherwise describe as grown men over a crumpled piece of paper with a few dots on it and so on, making moves, and you know, so I don't know what to do here, you know. Okay, congratulations, you know. I give up after staring at this board for ages. And it's a really interesting game. And so Berlekamp wrote one of the chapters of our joint book on games about Dots and Boxes, the Dots and Boxes game. Then he expanded on that later and published a little book, you know, turned it into a little book on the Dots and Boxes game, which apparently has been very popular. I don't know whether it gets read by school children or not. I doubt it.
Has the play of Dots and Boxes been influenced by the theory of games?
It turns out that the Dots and Boxes game only needs this previous theory of impartial games by Grundy and Sprague.
Because it's an impartial game. Both players have the same options.
It is an impartial game, but it doesn't quite fit the theory, but the theory is tremendously useful. Berlekamp can set up a position on perhaps an 8x10 board or something, so that there are 80 squares to be, you know, fought over. And he can say, if, you know, the first player makes this move here, this particular move, then he keeps on moving correctly after that, then he should win by, say, 43 boxes to 37 or something. But if he makes any other move, the opponent will win by at least 63 to 17 or whatever it is. It's rather amazing that one can discuss, you know, these things so precisely. That's a thing I like, by the way. You know, this is a children's game. Nobody has ever really treated it as worthy of study, you know. And if you do treat it as worthy of study, it becomes worthy of study. You know, you can play at a much higher level. We were attending some conference on computation in algebra or something. Berlekamp challenged me
to a game of Dots and Boxes.
A game of Dots and Boxes. Well, actually, it was bigger than this. So what you do is you join two dots, either horizontally or vertically, that are adjacent, and then the other player joins. I'll play both of them for the moment. And then, you know, okay, so we alternate. And then perhaps one of us will draw the third edge of a box. It's not usually such a good idea to do that, because the rule says that the other player, when he completes a box, so I'm pretending it's me who's completing this box.
You put a J.
I put a J, which is my initial, and then I have another go. That have another go thing is very important. I might not want another go, but I have to have another go whether I want it or not. And then whoever gets the most boxes wins. And my co-author Elwyn Berlekamp challenged me to several games of it, in fact, and we played on this board of 16 boxes, 4x4 in boxes, and he won every time, damn it. And he usually won by, say, 12 boxes to 4, or if he was a bit better, it would be 13 boxes to 3, or if I was a bit better, 11 boxes to 5. But, I never came near 8 to drawing this game. And then he confessed, what he was doing, and we decided to write a book on games. I discovered the surreal numbers, which came out of games, and I decided to write my book on numbers and games, which described the surreal numbers. And that I always think of as the book that I wrote in a week, which isn't quite honest, but it has a lot to be said. What was happening was I was teaching a lot. I had to, because I wasn't properly established at Cambridge, and I was supporting my growing family on piece rate teaching, essentially. And the term was about to start, and I knew that when it did start,
You couldn't finish your book.
I wouldn't be able to do much writing, So a little bit before term started, I started off writing this book. And I took my typewriter and I sat it on the table by the window of my college room, and I typed from roughly 8 in the morning to 12 midnight. And after a week, I roughly had this book called On Numbers and Games. And the reason I wrote it so quickly was partly because the numbers which arose out of games became very much more interesting for me, and it didn't seem to fit into the book that Berlekamp and Guy and I had planned to write.
Which was more about games.
Which was more about games, and more about games that didn't give rise to numbers. There were certainly some things that did. And I wanted to get this number stuff out of the way. So I wrote it. And then I didn't do anything with it for about 18 months. Every now and then I said, put table here, or add cross-reference to chapter ? Or solve this game or something. There were all sorts of notes like this, which meant it was rather unfinished. Some of it, by the way, was written before. One chapter, or 2 chapters, were written with the idea that they were to be published as papers, and I had never published them. So I edited them into chapters of this book and so on. And then after it sort of stewed around for 18 months, I took it out, edited it a bit, supplied all the missing things with some help from Richard Guy, and then added a last chapter that sort of summarized it all. Oh, by the way, when I wrote this book, I sent a letter off to my co-authors of Winning Ways, and I said, last week I wrote a book. That was the first line of it. And then I said, since it overlaps with our proposed book, I think I'd better tell you about it, and so
And I did. And then Elwyn Berlekamp wrote an absolutely furious letter back, which he couched in the third person, you know, if Dr. Conway imagines that so-and-so, I don't know. And he threatened to sue me because he thought I was taking material from the book we proposed to write and sort of appropriating it to myself. And so I wrote a letter back. It took me ages to write this letter back. But anyway, I wrote a letter back trying to calm him down and so on. But I didn't hear from him. And then I walked into the Xerox room in the math department at Cambridge, and he was living in California. And I saw him.
And you thought he'd come to get you?
No, I was very shocked. And he looked a bit sort of oddly at me and so on. And he said, I suppose you got my letter, you know. I got yours, you know. Let's call a truce or something. And anyway, we made it up, and so to speak, we've been the best of friends ever since. He conducts every now and then in Berkeley, where he's a professor of two distinct things, mathematics and electrical engineering. He conducts a sort of summer school on games. I'm not quite sure what he calls it. And he usually organizes a Dots and Boxes tournament and a domineering tournament. That's another game. And for the Dots and Boxes one, there's a prize of $1,000 for whoever wins the tournament.
Does he enter?
Sorry?
Does he enter?
No, he doesn't enter. The way he appears in it is rather interesting. This place is, this sort of meeting is attended by all sorts of bright mathematical graduate students from, all over the place. And of course, they're all keen to win this $1,000 prize. And so Dots and Boxes you see being played all over the time at meals and so on. And some of them are sitting up overnight analysing it or using computers to suggest strategies and so on. Anyway, that prize gets awarded, but then after you've won the tournament, you get the right to challenge Berlekamp to a similar little tournament.
For $1,000?
Yes, if you win that one, you get another $1,000. And nobody has ever beaten Berlekamp in this second stage. He's the sort of acknowledged champion of Dots and Boxes in the world. When we wrote our joint book, he didn't actually do all that much of the writing of the text. What he did rather, and what he's extremely good at, is finding out what goes on in a particular game, what you're really fighting about. So in Dots and Boxes, you think you're fighting about the number of squares.
What are you really fighting about?
You're really fighting about who gets the last move before the squares get opened.
The last move before the first square is taken.
Yes, essentially.
And that's a bad move to have.
Usually, when the first square is opened, so to speak, the player who just opened it is the loser. Every now and then, it's a good idea to sacrifice a square during the early part of the game, so that when it really comes to the end, you won't be the person who opens it and so on.
That's quite similar to a game called Reversi, where you fight over the first person to take a corner.
Yeah,
and occasionally you sacrifice one.
I used to play Reversi with my daughter, actually, and she usually beat me.
There's this poem, it's by Keats, in which he talks about unraveling the rainbow. His point is, I think, that one shouldn't try to explain the rainbow. It's a beautiful object. One should just appreciate its beauty. But in my experience, if you know more about something, you appreciate it more. And the rainbow is a particularly apposite case because it's absolutely fascinating what happens to form a rainbow. Lots of people sort of think they know how the rainbow is formed, but very few people actually do. It's a standard topic in high school textbooks, but what they say about it in the high school textbooks does not explain why the rainbow is formed at all. It does explain why it's coloured, if it exists. I didn't realize I was ignorant about why the rainbow existed until one day I looked up in the sky and saw what was apparently a straight piece of rainbow. In fact, I was sitting inside and I thought it was a defect in the glass window I was looking through. And it wasn't. I moved to another window.
And saw the same effect.
Saw the same effect and thought, oh, well, this is the same batch of glass, probably. So I had to go outside. I went outside and looked up, and my God, there was a straight rainbow, apparently. And then a former student of mine, he was probably still my student at the time, came past, and I sort of pointed it out to him. And then John Nash, he came by and saw it. So we assembled 3 witnesses. It turned out to be a sighting of what's called the third rainbow. When you have a raindrop falling in the sky, if a ray of sunlight enters it and bounces once, that's the first rainbow. If it bounces twice, that's the second rainbow. That gives the second rainbow. If it bounces 3 times, it's the third, and so on. I read about this a long time ago at the age of, I don't know, I was a teenager probably, in a book called Teach Yourself Meteorology. And it said, the third and fourth rainbows are occasionally seen, but the fifth never.
And did it comment that the third is straight, or is it always straight?
No, it's got a very large radius. It's about 70 degrees, and it's about the sun rather than about the counter-solar point, which the first and second are. And 70 degrees is quite close to 90 degrees. I mean, if you think of the Tropic of Cancer or Capricorn, it's nearly a great circle. And if you're looking from, so to speak, inside the Earth or something, a circle of radius 70 degrees looks straight, especially if you only see a portion of it. So that's what I saw. More modern books tell you that the third and fourth rainbows are never seen. And that's nonsense. The thing I saw was the fourth rainbow. I'm sorry, not the third. The third rainbow I saw later when I visited Lisbon. And by that time, I sort of understood a bit more about rainbows. And so I knew what I saw, which was quite amazing. The plane was flying towards the sun as it landed in Lisbon Airport, and it went through some cloud. And just as it went through the cloud, I saw what looked like a left-hand parenthesis out of my window in rainbow colours. And now I knew enough to tell that was the third rainbow.
And are the first and second visible at the same time?
Yes, they're often visible. I've seen them a lot of times in Oregon, where some of my wife's relatives live, and it rains a lot. You often see both rainbows at once.
Growing up in the rainy northwest of England.
Yes, I used to see rainbows a lot. I saw an absolutely beautiful rainbow once. I was staying in Hobart, Tasmania, and I suffer from insomnia, still do, but it was particularly bad at about this time. And I found that there was a coffee shop that opened at 6 a.m. in the town, and I was in some university apartment outside town, and I walked down into town every morning. and there's a mountain that overlooks Hobart, and it's always raining at the top of this mountain. It's really rather nice. And as I walked, the sun was behind me, so the rainbow was in front of me. And the rainbows, I usually saw double rainbows there. Absolutely beautiful. I mean, really lovely. And you see more of it because you don't normally see a rainbow at sunrise and even slightly before sunrise, or correspondingly at sunset. So, and you don't normally see them then somehow. Every morning I saw this rainbow. It was really rather nice. This pair of rainbows, I should say.
I wonder if you can give us the
Well,
diagrams
yes.
here.
I thought it was a defect in the glass, you know. So I moved along to the next window in the corridor I was sitting in, and that glass appeared to have the same defect, so I thought it was from the same batch of glass. But, you know, when I stood up, it moved in the way that it would if it weren't a defect in the glass. But I wasn't sure. So eventually I went outside and looked up at the sky, and there was this straight piece of rainbow. And I had no idea what it was. I mean, I thought it was something, you know, rainbow-like, because it looked rainbow-like, apart from the straightness. But then I realized that I did not know how the rainbow was formed. This is a little raindrop high in the sky, and there are lots of them, of course. And meanwhile, let's suppose the sun is over there, you know, horizontal, and then the picture you see in the textbooks is it's this rainbow is refracted a bit, then reflected, and then refracted again. And so the net effect is, let me draw this raindrop very small, the net effect is the light comes out not quite opposite to where it went in, but at 41 degrees. The trouble is that isn't an explanation because it's just not true. If you take this sunbeam here, it happens to hit straight on, it comes in, bounces, and goes straight back. And so we would see that piece of sunlight directly opposite to the sun, not at 41 degrees to the counter-solar point. But it depends where exactly the angle it's bounced through. It depends on how high up in terms of the radius the sunbeam hits it. And so imagine that we shone some kind of beam horizontally and then we moved it down steadily. What would happen to the emerging thing? And the answer is this. Suppose the counter-solar point is just there, then if this height that I'm mentioning is 0, which means it's hitting directly face on to the raindrop, it comes out at the counter-solar point. But then, as the height varies, it increases and then it decreases again. And guess what this maximum angle is? 41 degrees. And in mathematics, we're quite accustomed to the fact that when a function turns round and has a maximum, then that maximum is also a stationary point. In other words, most things that come in at near the condition that leads to the maximum emerge very near the maximum. Now I'm looking at the rainbow. This isn't the raindrop anymore. The one that hits straight on emerges there. Ones that hit
Close by to
fairly near straight on emerge in this little circle here, and so on. and then quite a lot of them emerge very near this thing, and then if they, then some of them emerge at the maximum, and then it starts decreasing again. And so what happens is there's a concentration of light near the maximum, and anything that bounces once inside comes out somewhere inside this disk, and a lot of it comes very near the perimeter of the disk, and that's the 41-degree thing.
And what about this fourth rainbow that you mentioned?
Sorry?
You mentioned you saw a fourth rainbow.
Yeah. Well, you see, if it might bounce more than once, bonk, 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 and emerge. If it bounces twice, the corresponding concentration happens at about 52 degrees. And so you see two rainbows quite often, one surrounding the other. I saw one quite recently. A double rainbow, they often call it. It's really two separate rainbows. And there's one thing that they do say in the books, which is that different colours emerge at different radii. And for the first rainbow, the red part emerges outside, and the blue part emerges just inside. These are the regions where, the concentration of colours happens. For the second rainbow, it's the reverse order. The red part arises inside, and the blue part outside. And by the way, the concentration effect, anything that hits, any sunbeam that hits the thing and bounces twice emerges outside this thing. And this gives rise to an effect that was noticed by Alexander of Porphyry, I think, in about 180 AD. This part of the sky between the two rainbows, look, when you see two rainbows again, is called Alexander's dark band, because the sky appears noticeably darker, because anything that hits a raindrop is taken out of this region and put either inside this circle if it bounces once, or outside the outer circle if it bounces twice. And theoretically, oh, by the way, that's quite interesting, because why isn't there, a question I've never seen asked by anybody else, why isn't there a zeroth rainbow, which is caused by things, which would be caused if it worked, by things that don't bounce at all inside. They're just refracted when they hit the surface first, then refracted again when they leave the raindrop. They're certainly bent through an angle. But the answer is that angle is just monotonic. It doesn't have a maximum or a minimum. So there's no particular thing at which the things are concentrated. But it can bounce 3 times or 4 times. And this apparently straight rainbow that I started by saying that I saw once was in fact a case of the 4th rainbow we worked out.
And you get that from the colour arrangement?
Well, yes. What happens is, let me redraw this picture a little bit. I have a mnemonic, which is, if the number is odd, the sun sees red. So you must remember that the sun is outside this circle. So it sees the red part. But if the number is divisible by 2, the sun sees blue. I believe in these mnemonics, by the way. They really do help you to remember things. So there's the second rainbow. Now the third rainbow is so big in these terms that it's actually on the same side of the sphere of directions as the sun is. That's one reason why you don't see it so often. So I've now seen all 4 rainbows. The 5th one is around the sun, and it's a very small circle around the sun, and so it's never been seen.
So I think you started, professional life as a number theorist, as Davenport student.
Yes, Davenport was a very well-known number theorist at the time. I started off talking to Davenport. I mean, when he agreed that I could become his student, and I regretted it afterwards. I sort of chatted and told him how results in analytic number theory, of course he knew, but I mean, started holding a long time before we could prove they held, And I've always thought of it as an appropriate punishment, the topic he gave me to think about.
Waring's problem.
Waring's problem, yes. Waring said in his Meditationes Algebraicae or something, in 17-something, that every number was the sum of 4 squares, 9 cubes, 19 fourth powers, and so on. And then this statement took a long time to prove. And when I got interested in it, only the 4th powers and 5th powers remained to be done. And
is that because he didn't say what happened beyond 5th power?
Well, he did. He didn't actually say what the number was for any powers, but that had been worked out, essentially. Davenport gave me this problem of finding what's called little g of k, for little g of 5. That is to say, every number is the sum of 37 5th powers. And I did no work on this problem for ages. And I used to turn up. We had a regular appointment Thursday mornings at 11 o'clock or something. And I would turn up and devote about 5 minutes as I was walking to the meeting place, trying to think of something I could say to Davenport to persuade him I'd done some work on the problem, which I never had. And of course he wasn't fooled. I was quite often late. Davenport was tremendously polite. And if I was 5 minutes late, he'd say, I only got here a minute ago myself. He had been 4 minutes late, in other words. Once it got up to about 20 minutes late I was, and, he had only been there for 5 minutes. He was a quarter of an hour late himself. And then one time, I forgot, and this really is true, I forgot to go entirely, and I got a little letter for him apologising for not being there, because it was such a nice day. He'd taken his wife and children to the seaside or something. So he said, and that's that. But anyway, at the end of my first year as Davenport student, well, I thought I had really better do some work on this problem, So I went home, went again to the Central Reference Library in Liverpool, stayed there for 12 hours every day from 9 a.m. when it opened to 9 p.m. when it closed. And my God, I solved this problem. And that was pretty good. It was after 1 year, and a PhD problem normally takes 3 or more years, And then I got back, and he said, well, now, Mr. Conway, have you done any work on our problem or something? And I said, yes, And, of course, he was accustomed to my saying yes. He didn't believe it for one moment. He said, did you make any progress? And I said, yes, well, actually, I think I've solved it. And he was a bit taken aback. And he said, mathematics is a subtle subject, he said, and it's quite easy to think you've solved a problem unless it's written down, you know, it's not reliable. He said, did you by any chance write it out, you know? Expecting the answer no, of course, or the dog had eaten it, you know. So I said yes. And he said, have you got it with you? You
And
know?
you said yes.
I said yes. And then he said, well, may I see it? Yes, you know. So I handed it to him, and I had really taken care to write out this thing, you know, as well as I thought possible. And he said, didn't quite expect this. I'm possibly inventing a few of the words I'm using, but this is the general impression. He said, well, I don't want to look through this, I'm afraid, with you sitting looking over my shoulder. So if you don't very much mind, I'd prefer if we call this meeting off now. I'll look through it in the next week and give you my opinion. So, of course, I didn't mind. So next week I turned up, and then he had his bit of fun with me. He said, well now, Mr. Conway, I've looked through your document. I'm afraid I have to tell you there are some mistakes in it. I just sort of, you know, I had taken care to make it as perfect as I damn well could. And he said, so he waited for a little bit, you know, to achieve the effect. And then he said, but they're patchable, you know, nothing serious. Oh, God. So we went through it. And at the end of this, I sort of rather hoped for some kind of congratulation. After all, I'd solved this PhD problem in 1 year.
And it was an old problem. It had been
And
around
it's a
200
good
years.
old problem, yes. It's been around since 1771, I think, was the date when Waring formulated it. But, you know, I was, as I say, rather expecting some congratulation. And what he said was, well, now, Mr. Conway, what you have here is a poor PhD thesis. And so, again, he was having a bit of fun with me, really. I mean, he hastened to explain himself. What he meant was, if you do nothing else, which I strongly suspect may be your intention or something, this will get you a PhD, you know. But you really should do something else, you know. And after that, we used to go along and talk mathematics and the philosophy of mathematics and so on. And actually, my interests changed. I stopped being interested in number theory and started being interested in mathematical logic and set theory and so on. And in the end, I never submitted that thesis. I submitted another one, which was more set theoretical. And
So that thesis has never been published.
no. And what happened was a man called Chen Jing-run, Chinese guy, eventually proved that theorem, and he proved it a much better way than I did. In fact, I just didn't contribute anything to that. It was all Davenport's ideas, and I just did what he told me to, you know, and it worked.
And were you concerned with the small cases?
Yes, that was what it was all about.
The big cases had all been done.
Yeah, that's right. Sufficiently large numbers had been done.
And probably they need a much smaller number
Yeah.
of powers.
Yeah, yeah, they do. I mean, for large numbers, 6/5 powers almost certainly suffice, although I don't think that's been proved. There's only one number that needs the 37.
And what's for one number?
It's 223. Everything bigger than 223 can be done with 36/5 powers.
But presumably you had to go a huge amount further. What was the cutoff that you had to reach?
Oh, I can't remember now. 10 to the 30 or something was the time at which the analytic methods worked. I mean, well, it was the time at which the previous analytic methods worked, you know. My job was to sort of tighten up the estimates and so on.
But then you were released from your obligation to
Yes,
talk to him
we
weekly.
just chatted, you know, and I eventually wrote a thesis on, it was called Homogeneous Ordered Sets. It was really about infinite numbers and order types, which are a sort of generalization. You know, when I started teaching in Cambridge, it was as a mathematical logician. The resident mathematical logician was just retiring, a Mr. Steen, very interesting guy. But again, you know, I got trapped. My interest changed again, and I suppose that was when I got interested in group theory. And then I moved from Cambridge to Princeton. I thought I was just giving a colloquium talk in Princeton. And my wife was with me. And as we went into lunch at Prospect House, the chairman of the mathematics department said, "I'd like to talk to you about your future." And I turned around and whispered to my wife, I said, "I think he's going to offer me a job. What do I say?" She said, "Don't say anything. String him along." When he actually did offer me a job, I said no immediately. And he was a bit taken aback and said, "Well, don't say no quite so quickly," he said. "Come along as visiting professor for a year, and we'll ask you again, you know." And so I said, "Yes, okay, as long as I'm not building up any moral obligation or anything." He said, "No, that's understood, you know." So then I came and for that year. And my friend Richard Parker said, "You're not coming back," he said, as I went off. And I said, "Oh, yes, I am. I've no intention of staying in Princeton." Then I discussed it with my wife a lot. We agonized over it for more or less the whole year. And at one time, I had this great idea. I thought, look, as far as I'm concerned, it's 50-50. The rational way to settle this
Just to toss a coin.
is to throw a coin, yes. So I had this great idea of having a little party for a few friends and then promising to obey whatever the coin said, you know, before witnesses, before the coin was thrown. And that's that. And my wife said, "Don't you dare do that." She said, if they hear about it, both institutions will be offended. And she was right. In fact, you know, she was more sensible than I was. In fact, any woman is more sensible than I am. And so we didn't have that party. We just went through more agony trying to decide, you know. And then in the end, I decided to stay in Princeton. And by and large, I've been fairly happy here, you know. My unhappiness at various times has been due to the breakup of my marriage with Larissa, more than anything else. Oh yes, there was something else. I didn't feel I was being used adequately as a teacher.
At Princeton.
At Princeton, yes, for quite some time. In my first few years, I was given sort of peripheral courses, like the development of mathematical concepts and so on, because, you know, I'm fairly interested in mathematical history. But I have tremendous respect for good, solid classical mathematics, you know, linear algebra, analysis, and so on. And I have firm opinions about how it should be taught. Now I regularly teach, you know, some standard courses. But unfortunately, you know, I'm being essentially pushed into retirement, which I don't want to do. I'm going to miss teaching tremendously.
Moving to Princeton also must have changed the direction of your work.
Yes, it did.
You lost the group theory colleagues.
The atlas of groups, that was something that I spent with my co-authors. There were 5 authors in all. The last 15 years of my time in Cambridge. Every now and then we got guilty of playing backgammon and did an afternoon's work on the atlas, and then that gave us the license to play backgammon for the next 3 weeks. Mind you, we discussed things all the time, you know. During the last year, we actually worked a lot on the atlas, tremendous amount. We had an arrangement whereby a man came from Oxford University Press, who were publishing it, once a month, and we delivered 25 pages to him each month. And that was quite exhilarating.
And those were the pages with character tables at that stage?
Yes, they were mostly character tables, but they had other things in. We would take over the common room the day before this guy was coming. There were a whole lot of chairs, you probably remember it, and we would assemble the material to go into one page on a chair, and there were 25 chairs, you know, therefore, for 25 pages. We would set it all up and then conduct a walkabout where we discussed each of the individual pages, you know.
And they're quite big, and you put together computer printouts?
Yes, they were very big. I mean, in the original versions, they were very big. Then we'd leave those on those chairs overnight with great instructions, do not disturb, and so on. And the next morning, this man would come, and we'd have another walkabout with him, talking about the particularly difficult points in the printing and so on. And then he would also deliver the previous month's pages.
So he took them away for typesetting? And
yeah. And, you know, we'd look at the previous month's pages as well. And that went on for the last year, roughly, of the production of the Atlas. And we worked very hard on that, because one of the things is we kept on discovering mistakes, errors in the Atlas. Oh my God, it was so tough, you know. And then, anyway, and the rate of discovery of mistakes rose as publication date came closer, you know. So it was quite strenuous. The math department had to give its sort of annual report to the Science Research Council, or the DSIR, whatever it was called. In our year, they just sort of said, the Atlas is what was produced, you know. It was the great thing. I always felt like a rat leaving the sinking ship. Not that I'm saying that Cambridge was a sinking ship, but I wrote the introduction to the Atlas in November 1984 and came to Princeton in the start of the academic year 1985. You know, we had a strong group theoretical school, but I won't say, I mean...
It's kind of died out since you left
Cambridge. It died out astonishingly quickly. Robert Curtis had already left. He was my first co-author to go to Birmingham University.
Rob Wilson left shortly after you.
Wilson
also
left.
to
The only
Birmingham.
one who's still around in a sense is Simon Norton in Cambridge. But Simon Norton hasn't got an academic position in Cambridge. He just lives there and has an office, but that's all. Group theory, so to speak, came to an end, more or less, in Cambridge. And And then it came to an end for me too, because for a year I didn't want to see a group again. I'd had so much hectic involvement during this last year I was speaking of that, I was sick of them. I knew I'd be interested in them again, but I didn't want to see a group for a time. And then also I came to Princeton, and in Princeton I was really rather surprised, because at that time, there was this great theorem, the classification theorem, that was being proved by mathematicians all over the world.
It had been proved, in fact,
Yeah.
4 years before,
Well, yes, but I mean,
modulo some big gaps. But
yeah, in almost every university I went to, there were 2 or 3 people who were working on the classification. And then when I came to Princeton, there was nobody who knew anything about finite groups, essentially, which was rather surprising, because Princeton, is an excellent university with a fantastic mathematics department. And so I thought, I should start a little group theoretical school here, But the life of a graduate student is 3 years, and it takes about 2 years to learn all the stuff about finite groups that in Cambridge everybody grew up with, because there were a number of people interested, and we were regularly talking about it and so on. So what happened was, I did have a few students, and I interested them in groups, and the monster group in particular. And then after 3 years they went away, and I realized it was going to be an uphill struggle, While I was still in Cambridge, I collaborated with Neil Sloan to a certain extent, and about sphere packings and codes and lattices and things. And he and I planned to write a book. And we had a number of joint papers, and I bound these joint papers at the English equivalent of Kinko's into a volume, and I used to carry it around with me. And Neil rather admired this volume, and I said, well, why don't we publish it? This was when he was on a visit to Cambridge, and we went down into the basement, which was being remodeled or something, and there was a paper towel machine on the wall, and I pulled out these pale brown paper towels and wrote the chapters, the titles of about 20 of our papers on them. And then we sorted them into order on the desk and called them chapters instead. And it took 20 minutes. And I said, there we are, we've written a book in 20 minutes. That must be something of a record,
And what's more, the book is tremendously influential and has had
It is
fantastic
now, yes,
reviews.
But it wasn't the same book that we wrote in 20 minutes, because then I came to Princeton, and Neil lived just along the road in Highland Park, which is essentially New Brunswick. And he would come every Thursday. He telephoned me while I was still in Cambridge and said, I think we ought to uniformize the notation. Our papers were written at different times in different notations. Don't worry, I'll do all the work, he said. So he did all the work of uniformizing the notation.
And you let him do that?
Yes. And then, another time there was another telephone call, and he said, I think I should write a little chapter between the first 4 and the later ones, changing the theme, Don't worry, I'll write it, you don't have to do anything, Well, this went on for some time. And then when I came to Princeton, he would turn up every Thursday and slave drive. I mean, he would make me work on this book. So what started off as the 20-minute book became the 7-year book. And they were 7 years of regular torture every 7 days, roughly speaking. He would arrive at about 10 or 11 in the morning and stay till 7 or 8 at night. As a result of that, it got a lot better. You know, it was pretty good after 20 minutes, but it was tremendously improved as a result of Neil's work on it, and it got rave reviews.
Best book. on the
Yeah,
best.
yeah. There's one review. Giancarlo Rota said, "This is the best survey of the best work in the best part of mathematics. It is written by the best people, will attract the best students, etc., etc." So I call that the best review. Although it's not actually the best review. There was another review
Of the same book.
of the same book by a guy called Forney, who started off by saying that this book reminded him of the six blind men touching the elephant. You know, one was holding its tail and another was holding its trunk and so on. And they basically described different animals. You know, nobody could have an impression of what the whole thing was like. And he compared this book to that. You know, nobody can follow the whole lot, but there are different people who can follow individual things. And then the final sentence, my God, it was fantastic. It said, "There is nothing else like it. And as an intellectual accomplishment, it is breathtaking." Oh my God. And this arrived at a time when I was tremendously depressed. I actually attempted suicide in 1993. And I was still suffering from clinical depression. And these two reviews cheered me up no end. The best one, I copied out in black marker pen on a big sheet of white card, except every time the word best occurred, I changed to red marker pen, and I hung it up on my wall. And when I got, particularly depressed, it cheered me up no end. However, I shouldn't go on boasting for too much longer, although I'm quite good at it.
Do you feel you missed the chance to explain the monster by leaving Cambridge? There was a lot of momentum built up on the group.
Yes. Well, perhaps I'd better say what the monster is.
And why it's called the monster.
The monster is the largest of what are called the sporadic simple groups. And groups are the mathematical way of talking about symmetry. And so we're essentially studying different fundamental kinds of symmetry. And there are 26 or 27, if you count them rather differently, sporadic simple groups, of which, some of them are my groups, the one of the symmetry group of the Leech lattice and so on, that made me, into a jet-setting mathematician. But the largest of them all is this so-called monster group, which was discovered by Bernd Fischer and to some extent independently by Bob Grice. I would love to understand why the monster is there before I die. I've been saying that for more than 20 years now, and I don't expect to tell you the honest truth. I've given up now, seriously hoping. But every now and then, every 5 years roughly, I sort of think about it again and usually make some progress. But one of these times was when I went with my wife to a conference in Durham in England. And she was actually, I was the spouse for that meeting. She was a mathematician. She attended the lectures, and I sat minding the baby outside, except every now and then when the baby fell asleep, I tiptoed into the back of the lecture room. During that time, I worked on this construction for the monster, based on an idea of Richard Parker, one of my co-authors of the Atlas. And I found this simple construction. I was
Relatively speaking.
Sorry?
Relatively speaking.
Relatively simple, yes. Grice was the first person to actually construct the monster, show that it existed. His paper was 113 pages long and mine was 13 pages long. Well, that's a bit cheating. It had some tables at the end of those 13 pages, which I don't count. That was the first of my real interactions with the monster group. Another one was when I discovered, with my friend Simon Norton, also a co-author of the Atlas, this moonshine phenomenon, which was, we wrote a paper called Monstrous Moonshine, which was about some very strange connections of the monster group with modular functions and so on. You worked on moonshine to some extent, and so did my Russian wife, Larissa. That's another interaction with the monster.
The Y diagram.
Yeah,
26
the Y
note.
diagram, the 26 note theorem, there are all sorts of things. Nothing has given me a feeling that I understand why the monster is there, you know, and I'd love to. I mean, everything is like this. Here's this amazing thing, maybe. Okay. What Grice did was study this amazing thing, supposing that it existed, and finding out all sorts of properties it had to have. And then eventually he sort of started looking for something with those properties and then found it, was able to construct it. But if he didn't think it existed before he looked, he would never have found it, you know. So his thing doesn't explain the existence. Actually, it uses the existence to construct it. Yeah. Then there's my student and our mutual friend, Richard Borcherds, who came rather closer than anybody else, I think, to understanding the monster. But I don't feel happy with what we've understood. It's such a beautiful thing and a natural thing. By the way, Grice criticized me very strongly for using the term monster for it. I wrote a postcard to Fisher, who was the first discoverer of the monster, saying something like, I've been thinking a lot about your monster simple group. He liked that name, and ever since then it's been called the Monster.
And the name has really been good publicity for the group.
Yes, I think it has. You know, Grice made the point, and I agree with him in a way, that to call it a monster suggests it's sort of ugly or frightening something. And I wasn't thinking of that at all. I was just thinking of it as being tremendously big, you know. Maybe a bit frightening in a way, but not ugly. Really a beautiful thing. But, you know, it's very strange. The way I think of it is there's a geometrical object, like the kind of star you might hang on your Christmas tree, you know, which is tremendously symmetrical. And however, it's very, very big. An icosahedron, one of the regular solids, has 12 vertices. A dodecahedron has 20. And they have 120 symmetries. You know, you can view them from 120 different positions, and they look the same. Well, the monster, it has nearly 10 to the 54 symmetries, a huge number. And where does it live? Well, the geometrical object that supports it is in 196,883 or 4 dimensions. You can't really think of this monster, and yet somehow, collectively, we mathematicians did, you know. And I don't understand why it's there, and I really want to.
In a sense, we don't know the object it's acting as symmetries on is the problem.
No, not really. I mean,
We know the
it's-
symmetries, but not the object.
Yes, in a way. You know, there is an object that's being constructed, but I feel that there should be a simple way. I think that something that is so fundamental, so natural, ought to have a simple definition. And, you know, I'm still trying. But every time something has turned up about that, and I feel, you know, happy to have discovered something, but it's never an explanation. And to tell you the truth, I really have given up, you know, on finding an explanation. No, not given up, you know, but, you know, it might turn up, and that's, you know, I hope to be kept alive, but I honestly doubt if it will. It's, you know, I think it will eventually, you know, after a century or two.
I've written a list of fractions up here. What you're told to do is start with the number 2, and then from now on you multiply the number you have by the first of these fractions that gives a whole number answer,
So you have to go a long way.
which in this case is m, and so you'll get 15, which I'm going to write as 3 times 5. And now, so the only possibilities are those whose denominator divides 15. And if you look along, there are none of those.
55.
Oh yes, there is. There's 55. And so we'll, by the way, we used, which did we use? 15
M.
over 2. We used m. And now we'll use n and get 3 times 5 squared times 11. And now
E.
we can use e because there's usually a big prime in here, where big means 10 or more. The big 91 isn't prime, it's 7 times 13, so the big prime is 13, and that's not 11. The big prime is 17, the big prime is 17 again, the big prime is not, the big prime is 11 here. So I'll use e, and I'll get, that'll rub out the 3 and the 11, and replace them by a 29. And then the next one was the first number for which the denominator, f. So we'll use f, and so on. That's the game. It's not a very interesting game to play. So what you're told to do in this game, which I call prime game, is look out for the powers of 2. And, well, we've had one at the beginning. Let's not count that. Eventually we find 2 squared. I'm going to write in red here the stage, 0, 1, 2, 3. By the time we get to 19, we find 2 squared. It's a power of 2. So we take a photograph of it with our Brownie box camera or something, because we probably want to show it to our grandchildren. And then at stage 69, there's another power of 2, 2 cubed. That happens at stage 69. And then at stage 200 and something, we missed 2 to the 4th. I wonder why. We get 2 to the 5. And then rather later, we get 2 to the 7th. And most mathematical readers will guess what the sequence 2, 3, 5, 7 is. Especially, however, I gave the game away a little bit before. This is a computer program for computing primes. You see 2 to the nth if and only if n is prime. And I got interested in this a long time ago. It's part of a sort of continuing interest in ways of calculating things. I'm not terribly interested in doing it efficiently. I'm not a very practical person. I like theorizing about it. And it's an interesting remark that any computable function of integers, taking integer values, can be computed in this sort of way by a list of fractions. I wrote down once in my little paper on this subject a particular list of fractions that if you feed it with 2 to the n, the next power 2 you'll see is 2 to the nth decimal digit of pi.
Oh, so you start with 2 to the n instead of 2.
Yeah, if you start with 2 to the 0, you'll get the 0th decimal digit, which is the one before the decimal point, namely 3. 2 to the 1 gives you 2 to the 1 again. 2 to the 2 gives you 2 to the 4th, because the second decimal digit of pi is a 4. And it goes on 3.1415926535897932384626, etc. And it always gives the digits of pi. However, it's a very, very slow program. In fact, if you fed it with 2 squared and waited, then I think you'd be waiting until after the universe finished before it would compute it. But theoretically, it computes digits of pi.
And any possible program can be written in this language.
Yeah, essentially. Any program, any computable function from integers, from non-negative integers to other ones, can be computed by just a list of fractions like this. I wrote a little paper called Unpredictable Iterations about that. So, you may have heard of this 3n plus 1 problem. Do you know it?
Yes.
This is a nice little sort of game you can play. Well, it's a nerdy sort of game. You take a number. If it's even, you halve it. If it's odd, you multiply by 3 and add 1. And the conjecture is, it's due to a man called Lothar Kollátz, German, who dreamt it up around 1940, I think. The conjecture is that this always ends in a 1. And it's pretty clear that it does, but I don't expect anybody to be able to prove that. It's been verified for numbers less than 1 billion. Something like that, anyway. Yeah. That was one of my recurring sort of themes. The simplicity of ways of calculating things. You know, I read the standard sort of books about great discoveries in mathematics when I was a student, and Gödel's theorem is this very famous theorem that a formal system for proving things about arithmetic necessarily can't prove everything that's true unless it also proves some things that are false, and so on. And Gödel proved this theorem using Gödel numbers, which are ways of numbering essentially computer programs. And the books always used to say, of course, the Gödel number for any statement that's interesting will be enormously large. And I sort of didn't see why it had to be. Or, various things like that. And so this list of fractions
Could be a number.
it could be, it could be coded up into an integer, and it wouldn't be all that large. And, that one computes primes. So I was interested in simple ways of computing things. And that led me, at a different time, to my interest in this life game. When I was a student still, I read Martin Gardner's columns along with all the other sort of scientific students, really. And he wrote this column for many years in the Scientific American called Mathematical Games. and he would discuss various things. And my friends and I read this column and played the games, with each other and so on. And then I started writing to Martin, and in the end, what happened was this. I would keep a roll of paper in my typewriter, a good old-fashioned typewriter, sit-up and beg type typewriter, and every now and then I'd say something that was interesting us. Maybe a comment on Martin's last month's column, maybe some kind of game or puzzle that we were playing with, and so on. And then I'd write a page or so and turn the roll of paper around and so on. And when it got to a suitable length of 5 or 6 feet, I would sort of fold it up, rip it out of the typewriter, fold it up, and send it off to Martin Gardner. And then he started using these things as filler for his column. He did an amazing thing. He wasn't a mathematician. He didn't have a mathematical or indeed a particularly scientific education. He did philosophy at Chicago. But he wrote this initial article on hexaflexagons, little folded pieces of paper, which wasn't one of his columns, actually. It was an article in the body of the magazine. But it got more mail than any previous article in that magazine. So the editors asked him, could he have a regular column, conduct a regular column? And he was short of money and interest and so on, and so he said yes and launched himself off into this column, which he conducted rather wonderfully. He conducted this column essentially by having correspondence with a number of people who, wrote to him after reading his columns, no doubt, and so on, with particular mathematical problems suitable for the column. And then he would digest what they said. And he used me, which really, I suppose, meant me and the people I was collaborating with in Cambridge. Every now and then, he would just look at one of these screeds of paper I sent him, again, every now and then.
With comment on previous articles.
With comments on previous articles or on what we'd been thinking of, some ingenious little puzzle or something. That lasted a long, long time. And then I got into the habit of going to see Martin when I sort of grew up and got a job at Cambridge and so on. I travelled across the Atlantic once every 1 or 2 years, roughly speaking, and I would stop at his place. At that time he had a nice address for somebody writing a mathematics column, 10 Euclid Avenue, Hastings-on-Hudson, New York. The first time I met him was very interesting. I took the train up and he met me at the station there and took me back home to his house, and then he had to collect his 2 teenage boys from school. So he took me up to what he called his den at the top of his house.
Left you there.
And left me there and said, I'll be back in half an hour or something. And he said, you can play with anything you like.
What did he have in there?
Well, he had all sorts of toys. Well, what I did, I pulled open a little drawer which was above a semicircular table that sort of stood out from the wall at one point. And I got a real shock. I almost screamed because a mechanical insect jumped out. And then it sort of walked to the edge of the table, and then it sort of felt around. There wasn't any more table, so it turned around and walked in a different direction. And this thing, very, very simple device, this thing walked around until its clockwork ran down, and that was a very nice little thing. But anyway, there were all sorts of toys in his den at the top, and his wonderful collection of 3x5 index cards, which sort of organized all his writings on such things. He came back And we went out to dinner. He had one or two people who were interested in meeting me and so on. And we made up a little party of 6 or 8 people. And we went to this restaurant in Dobbs Ferry. And it was a very sort of cheap place. There was a big deal table. Deal is the appropriate word, actually, because the waitress came round, an Irish waitress came round, and she dealt plates onto the table. And these plates came with something of a clatter, you know. And then she came round and dealt cutlery, knives and forks and things onto the table. Not carefully placing them, but, you know, here's a knife, fork and spoon for this person and then for this person. And Martin picked up his knife, fork and spoon, and he picked up his plate, and he dropped the knife and the fork and the spoon. They went right through the plate and landed on the table beneath. Well, of course, they didn't really go right through the plate. I'm describing the effect, what people saw, you know. Well, this waitress screamed. And Martin sort of looked around, you know, something strange happened. And then he picked his cutlery up again, and this time he sort of threw them through the plate, and they landed underneath it, and we all looked. And then he gathered everybody's cutlery and sent it in a continuous stream through the plate, and it piled up in a great heap underneath it. And I said to Martin, you must show me how to do that sometime. And he said, later, you know. And but then he never actually, oh, he did say, I'll tell you something about it right now. It was pretty dark in that restaurant, and I wouldn't have done it had it not been dark. But then he forgot to tell me that time, and
So that's all you know.
to ask him. And on some later occasion, he didn't know which trick it was he'd performed. He knew dozens of tricks, or thousands really. You know, he used to write in magic magazines, and one thing I discovered is that professional magicians had the same reverent attitude to Martin Gardner. They all read his columns in magic magazines at the time we were reading his columns in the Scientific American. He was a very, very learned man. I was reading one of his books only the other day, and I was struck by how much that guy knew about science, philosophy, you know, essentially everything. Very, very knowledgeable guy. Martin's birthday was October the 21st, I think, his 95th birthday last year. And this man at the publisher, whose name was Peter Rents, and I'd known him a long time ago, telephoned and asked me for a blurb for a new collection of Martin Gardner's columns. And he wanted to get it out in time for Martin's 95th birthday. I don't know whether they did get it out or not. Martin was actually collaborating on it. He kept on writing stuff, you know, right up till the day he died, practically. And Siobhan and I, Siobhan Roberts, who's writing my life story, and we were going to see him after the last gathering for Gardner, which was in March of last year. And she telephoned him to make final arrangements and got instead the director of the assisted living facility where he spent the last few years. And she said he'd died the day before. So it's quite interesting. You know, another woman telephoned me later the same day, which was a Sunday, and said, you know, Martin Gardner's dead. And I said, yes, I know, I just heard. That was on the Sunday. He died on the Saturday. And on the Monday, we read his obituary in the New York Times. Some of us did, anyway. Yeah, I miss that man. I was really looking forward to seeing him again. I haven't seen him for about 10 years, you know, before that. But it was always enjoyable, and he would show me a new trick. And so on. Every now and then I showed him a new trick. But there was another thing, you know. He taught me once how to tie a piece of string into a knot without leaving go of the ends. Well, again, one can't really do that, but it's how to make it seem that you're doing that. And we were chatting once, and he said, "Oh, there's a new way of doing that," he said. And he took this piece of string and went, "Ooh," and there was a knot in the thing. I said, "Martin, you must show me how to do that, you know." And I was mindful of this time when he had promised to show me how to do this other trick, and it never worked. So he said, "Okay, yes, don't worry, I'll show it to you now." And he did show it to me. And I practiced it. I could do it pretty well, you know. The trouble is, I forgot to do it again. You know, with these tricks that involve some cunning motion of the hands contain the memory. You know, it's no good sort of remembering the description of what goes on. You sort of do it until you practice it often enough. You've got to practice it sort of 20 times the first day, and then 10 times each day for a week, and then once a day for the next of the month, and so on. And then you've got to do it every month for the rest of your life, roughly speaking, if you had to remember it. And I didn't do that, and I realized, oh my God, I've lost it again, you know. That was really nice. Yes, tantalizing. Martin was always full of ingenious new ideas and tricks and so on, not necessarily his own. Oh yes, I remember one other occasion, the day of the week business. I don't know whether I dare to do it with no preparation. What date were you born?
15th of November, 1958.
Yes, okay, that was a Saturday.
That's right.
So I can still do it. How that came about is quite interesting. It was on one of my visits to Martin Gardner, and I got off the plane. It was at Kennedy Airport. It may have been so long ago that it was still called Idlewild. I don't really remember. And there was no Martin there. And I didn't know what to do. You know, I'm most disorganized sort of person. My life is perpetual chaos. You know, I walk in a cloud of chaos that always surrounds me. I didn't know a telephone number for Martin Gardner, nor how to get one. And even if I knew one, I wouldn't have quite known how to handle the American telephone system, you know, phones with, you know, coin slots and all that sort of stuff. So I sort of thought, I'll wait for an hour or two. Well, of course, I thought that after waiting for a quarter of an hour already, you know. Then I was trying to think of people I would know somewhere in New York who I could stay with if necessary. Anyway, I waited and waited and waited, and eventually, I think it was almost 2 hours later that Martin arrived, and he dashed up. He was out of breath. He said, I'm sorry, but when you've heard what I've found, you'll forgive me. I said, Martin, there's no question of forgiveness, you know. I mean, people have to forgive me every time for forgetting things, and if I demanded forgiveness from them proportionally, it would be terrible. It turned out that he'd been in the New York Public Library on 42nd Street, I think it was. And he had discovered an article by Lewis Carroll in Nature, which is now a serious scientific journal, but then was like Popular Mechanics, if Popular Mechanics still exists, or even if it doesn't. And it gave a rather simple rule for working out the day of the week. And Martin knew that the sort of Lewis Carroll fans didn't know about this article. So it was a new bibliographic discovery about Lewis Carroll. And he knew that because he was high up in the Lewis Carroll
And
Society.
he wrote the annotated Alice.
Yes, he wrote the annotated Alice and various other things. He published an annotated edition of The Snark, too. Anyway, so he knew they didn't know about it, and then he stood in line for the copying machine. This was in the days before Xerox machines. I don't quite know what kind of copying machine it was. And then as he stood in line, he realized he was going to be late to meet me. But by that time, he'd invested half an hour of his time in the line and moved quite some distance up in it. And so he thought, well, I'll just stay so much more. It'd be a pity to throw this time away, and so on. And it went on happening. You know, when he was just outside the copying room door, you know, he thought, oh God, I really must go. But then he stayed a bit and so on. And he told me all this as we were sort of zipping ourselves in.
And his interest was because it was by Lewis Carroll.
Yeah.
Not that it's an algorithm for the day of the week.
Yes, but it, you know, as we zipped ourselves into his car, he handed it me to have a look at, and he said, you know, it's a rather interesting way of doing this. You know, in his filing cabinet, he had a large number of 3x5 index cards, and when we got to his den this time, we looked, you know, for rules for working out the day of the week for any given date, and we found about 20 of them. And you know, we examined them, and this Lewis Carroll one was better than any of them. And but then Martin, as we were driving along, said, you know, John, you ought to work out a rule that's really easy and that I can teach my readers. Now, I had worked out a rule when I was a high school student, you know, but it wasn't all that easy, and it demanded a certain amount of arithmetic and so on. So anyway, I took this challenge seriously. Between 6 and 6:30, Martin and his wife Charlotte, one of them would say to the other, I think it's your turn tonight, dear. And then the other one would say, no, I don't think so. If you remember, I did it last night, you know. I sat there wondering what on earth they were talking about. And so eventually one of them lost this fight, you know, and toddled off into the kitchen and made 2 old fashions. I had never tasted an old fashioned before, didn't even know what it was. It's
So when
some
you
kind
were
of
there,
cocktail.
there were 3 of them. When you were there,
When
they
I
made
was there,
3.
yes, they made 3 of them.
And they brought them in, and we sat for half an hour sipping these things. And then Charlotte would begin to yawn and say, I don't know, this happened every time I was there. I don't know what's happened to me tonight. I feel terribly tired. So if you don't very much mind, I'll leave you 2 boys to yourselves and toddle off to bed. So she toddled off to bed, you know. This was perhaps 6:45. And then after she'd gone, Martin would survive until perhaps 7:30. And then he would yawn uncontrollably, and with great apologies for leaving me alone, would leave me alone. And so that was that, you know. I got quite used to this habit later on. One of the earliest times I visited with him, well, in fact, I was always billeted in the same room, and it was his room for interesting books, you know, his little library. And he said, this shelf is particularly interesting. He said, take any book down from this shelf. So I pulled a book down from this shelf. And he said, oh, that's an interesting one. Yes, read it and see if you notice anything odd about it. So I started to read. The language sounded a little bit formal, but in the end I said, no, I can't really tell, you know. And it turned out to be this rather famous book. It's more famous now than it was then, called Gadsby, which is an entire novel written without the letter E. And Martin's copy had a newspaper cutting in the back, which showed the author's typewriter. And it was a good old-fashioned Remington typewriter or something like that. And the guy had taken off the E key and sharpened the thing that supported it to a sharp point, so that if he ever accidentally hit the E, he bled, basically. And this article said a few things about him which I can't remember. But then, he had another book which was sort of a palindrome in words from the beginning to the end. The last word was the same as the first word, the next to last word was the same as the next to first word, and so on. He had, a little children's book that you could turn upside down and read it again, and it told a different story. He had all sorts of strange books in there. Wonderful collection of junk. And by the way, every now and then Martin had a column with 12 problems in it, often sort of little scientific things, sometimes purely mathematical, and so on. And many of the sort of objects that appear in those problems were in his house. At one time, he mentioned a rather clever sort of egg timer thing. There was one of these, things, two bulbs connected together, both of them, well, one of them filled with sand, which flows into the other one. And, but this one had all of that inside a transparent tube filled with liquid. And what you had to do is explain why, when it got to the end of its time, this internal thing suddenly floated up to the top, and hitherto, it had stayed still. Was it getting lighter or something? And the explanation was, when the top bulb was filled, it was sort of top heavy, and so it tended to lean over, and that stuck it in the tube. But then there was another one where exactly the opposite happened. While it was operating, it was at the top. But anyway, there were all these sort of funny things in his house. One of his books was called Mathematical Carnival, and I wrote a little introduction for it. It happened to mention a number of these things in the text of the book. So in my introduction, I sort of recall staying at Martin's house
And playing with the things.
and seeing all these actual things. I said, readers may expect that these are just theoretical, but no, they're all in Martin Gardner's house. He was one of the most interesting people I've ever met. This game, which you might call the 3x3 game, but which it's nicer to call the 2x2 game. It depends whether you're counting dots or counting boxes. This game turns out to be astonishingly difficult to play. And I have a fairly standard challenge, which is, if you were taking this challenge, you would play 10 games with me. You would choose for each game whether you played first or second. And if you won any one of the games, you're declared the winner of the tournament. By the way, there's a rule that if the boxes get divided 2-2,
The second player wins.
the second player wins. That's the tie-breaking rule. I sort of win it, I think, more than half the time. In other words, more than half the time, I win all 10 games, which you couldn't do. This game, which of course you're all familiar with, even if you meet somebody who comes from a culture where they don't play it, they would learn in a few games what you do and be just as good as anybody else, essentially. But with this game, it's strange. It takes such a long time to learn it. And it's very interesting. Well, that I learned in a way from Elwyn Berlekamp. But I'm better at this small game than he is. He can indicate positions, you know, in which there are lots of boxes to go and tell you exactly what the best move is and by how much you should win if you make it.
So you said Berlekamp was good at finding out what you were really fighting over in a game.
You know, there's a game that I invented actually called Hackenbush. And, well, first I'll describe the sort of uncoloured Hackenbush. You play it with a picture. I'm drawing a picture of a house, a rather simple house. Now, that's not a childish picture, because obviously this window here is going to fall down. There's nothing holding it up. So it's got to be a childish picture you play with. It's okay if you join the window on there, you know. Maybe you have a chimney and so on, and maybe there's a tree out here. And perhaps there are some apples on the tree and so on. And maybe there's a little doggy. Everything has got to be connected to the ground. And then the way you play it is by rubbing out an edge of the picture. And now, if I rub out that edge... Oh, by the way, each edge joins two little spots that are sort of marked clearly. If you rub out that edge, nothing falls down, because it's very strong steel this is made of, and it won't fall. But then,
if you take this edge, the whole tree falls.
If you take that edge, yes. Well, let's take that edge, and then the branch bearing the apple will fall down to the ground and just gets disappeared and so on. And the rule is that whoever makes the last move wins.
And this is an example of a sum of games.
Yes, it is. This sum of games, this is a game which has three parts to it: the dog, the house, and the tree. It's a sum of three separate games. And by the way, there's a more interesting version of it in which you have two colours. Red and blue are the typical colours, you know. And the player called left is only allowed to chop blue edges, and right is only allowed to chop red ones. And it's essentially the same thing. Well, now, if you consider this game directly corresponds to numbers. You see, suppose I have just a beanstalk of three blue edges.
It's good for the blue player.
Yes, it was called left, you know. And if over here there are two red edges, then left, who plays blue, will win. If they're the same number of each colour, then whoever starts second will win. So that's really the way Zero arises as a game. It's a game in which, any game in which the second player wins, no matter who it is, can win if he plays sensibly, is a Zero game. But now, well, I'm going to write down an equation. This is something we were talking about before. This blue edge, if that were all the game were, then it would be legal for left to make a move. Left, remember, removes blue edges, and that would finish the game. And it's illegal for right to make any move at all. That's what we call one free move for blue or for left. This turns out to be a half of a free move.
Because right can make a move if he goes first, but not if he goes
what
second.
happens is, perhaps I should subtract one from it. So I've now set up a half plus a half minus one, which should be 0. And indeed, that is a 0 game, meaning that whoever starts loses. You see, I don't know which you want to be. Let me be left for a moment.
Blue.
Yes.
So
Then,
if you start, you've got no choice.
If I start, I've got no choice. What should your move be?
Take the top one.
Yes, it's foolish to take this one down here, because then you leave the last move to me. So you take the top one, and then I am forced to take this one, and you take that one, and you win. So that's what happens if left starts.
And if right starts,
If right starts, what move do you think?
it's better to take this.
Yeah, that's right. And then what should left
You
do?
kill this.
Do this, and then right will do that, and left will do that. So whoever starts loses, so that's a 0 game. And all the concepts of arithmetic can be expressed in terms of games. I've only really talked about addition and order.
But there are examples of games, aren't there, that are beyond arithmetic.
Yes, there are.
But you can't get those of Hackenbush.
You can't get those with this red-blue Hackenbush, but you can with green Hackenbush. If a green edge can be taken by either player. It's possibly better if I pronounce that as either player, green for either.
And you have red and blues mixed with it.
And you have red and blues as well. Then it turns out that if you have a positive game, in other words, left can win over here in red-blue Hackenbush, and we add this green edge, it doesn't make any difference. Left can still win, no matter who starts, I'm sorry.
Because you want to take the green edge quickly.
Yes, that's true. If you have a negative game, in other words, one that's won by right, no matter who starts, then it's still negative if you add this green edge to it. But if you have a 0 game, remember that in a 0 game,
So this is a 0
the second
game with
player
nothing on
starts.
there.
We've got a 0 game set up there. It's not very interesting. But now the first player wins.
Yes.
So the value of this game is not a number, and we call it star. And however, star is less than 1. Oh, but it's also less than a half. And it's less than a quarter and a third, I could have said as well, and so on. And star is very, very tiny, but it's greater than every negative number, and it's confused with 0. And so it's an example of another type of game. And in this theory of games that's in my book on numbers and games, we found a whole lot of other curious values. And games constitute what mathematicians call a group. You can add them, subtract them. It's an partially ordered group, and it's very interesting. It contains every partially ordered abelian group there is in the world.
So the other thing with the board was lexicodes, but I don't know if you want to do that now.
Well, a code is a collection of things called code words, and you usually want the code words to be sufficiently far from each other in a certain sense. So these lexicographic codes, well, first of all, a code word is an infinite string of digits going off, but you can think of it as rather like a decimal number. So this is the number 0, which really its decimal expansion consists of infinitely many zeros, but we usually rub off those. And then comes 1, and then 2, and after some time you get to 10. Okay.
But you already had a 10 in the last digit. I mean, you'll allow any positive integer in the last digit.
Yes, with integral lexicographic codes, the digits are allowed to be arbitrary integers. Distance 3 means you're not allowed to have two code words that differ in less than 3 digits. The first word you are allowed is 111. It differs in 3 digits from this previous one. And now the first word that differs from both of those in at least 3 digits is 222. And we carry on doing that, and after a time we get n, whatever n you like. And then there is a word that goes 1012. That differs from all of the ones before it in this digit 1, because they were all 0 there. And whatever number you take here can only happen once in this thing. I mean, if I take 111, that agrees with it in this one place, as well as the one before the point and so on. But because these 3 digits are different, it can't agree in more than 2 places with any previous one. Then after that comes, if I have 1 naught, then it's too close to this one. It only differs in the last 2 digits.
You could have 1 1.
But you can have 1 1. Try it. But now I can't have a 0 here because it's too close to that one. And I can't have
A 1.
a 1 because it's too close to this
And you
one.
can't have a 2 because it's too
I
close
can't
to
have
the one above.
2 because it's too close to the one before it. So this must be at least 3, but 3 is okay. So there's no choice in what you do. And I discovered this astonishing fact that this lexicographic code, which I abbreviate to lexicode, is closed under a kind of addition. If you add 2 code words, you always get another code word. That's pretty obvious for the first few. If I take, say, this one and this one, then of course I'll get this one. And these are in the code, and so this one should be. It turns out, this is rather cheating in a way, that the addition is not the normal addition. And you can prove fairly easily that you add to 0 the way you usually do. And so if you take 1, 0, 1, 2 and add it to 0, these are all preceded by lots of noughts. Well, let's sort of take it 2, 2, 2. Then the sum of these two should be a code word.
1, 2.
And because 0 adds normally, that's 1, and this is 2. So this is something. Maybe I should have added 1, 1, 1. And then this would be 1, 1, something, something.
And it must be 0, 3.
It's got to be this one. And so you see that 1 plus 1 has got to be 0, and 2 plus 1 has got to be 3. And it turns out that, this theorem tells you what the addition has to be by the same kind of calculation as we've been doing. But then it's also got to be closed under multiplication, digit-wise multiplication. And the multiplication is really strange. It turns out that the addition is the same kind of addition that you use in the theory of the game of Nim. This really comes from games like Nim. It's also called exclusive OR by computer people. But the multiplication I don't think anybody ever saw before I noticed it. And it's rather peculiar. it turns out that 2 2s are, guess what, 3. And 2 times 3 is 1. So
3
that-
times 3 is 2.
Yes, and that tells you that 2 cubed is 1, because 2 times 2 times 2 is 2 times 3, and 2 times 3 is 1. At the time I discovered this, it was a very long time ago now, I didn't know it was going to work. I didn't have this definition of it as I've been telling you about. I had another definition, but it still didn't seem obvious that it worked. And I got to work out the multiplication table. 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. 0 multiplies in the obvious way. And so does 1. But 2 2s, as I said, are 3. 2 3s are 1. And 3 3s are 2. So that little part there is closed. If you take any 2 of 0, 1, 2, and 3, the product is 0, 1, 2, or 3. Then, sorry, that isn't a 12. That was a piece of chalk left on the board from some previous thing. 2 4s, it turns out, are 8, which surprised me a little bit, but because it was agreeing with ordinary arithmetic. And 3 4s are 12. And so I get 0, 4, 8, 12. And then, what are 4 4s? Well, it took me a good long time to work it out. And then, when I finally found the answer, it seemed ridiculous to me. And I remember I lay down on the floor and giggled and I was totally alone, waved my arms and legs in the air. It turns out that 4 4s are 6. And then I could work out what everything else was, what the product of any 2 numbers up to 15 was. And it's rather strange, you know.
So you use the distributive law beyond this?
Yes, it's distributive and associative and everything. It turns out, one of the things that really surprised me, I told you 2 was a cube root of unity. 8 is a 5th root of unity. And 8 squared is 10. And 8 tens are 14. In other words, the 5th roots of unity are 1, 8, 10, 13, and 14. How about 4? 4 is a 15th root of unity. How about 15? 15 is a 15th root of unity too. In fact, 4 and 15 are inverses of each other. Oh yes, that's a remark. This is actually a field. In other words, you can divide by non-zero things as well as multiplying and adding and subtracting and so on. And so that means that the reciprocal of every number here, in this new crazy sense, is another number. So what's a half? Well, I told you, 3 2s are 1, so a half equals 3. And a third equals 2. What's a quarter? A 15th. What's a 5th? I think it's 14. I'm not
Or
quite
13.
sure. No, it's... Oh my God, I got it wrong. So what I said was not true anyway, and what you said wasn't true either. Because 13 and 14 are 5th roots of unity, whereas 5 is a 15th root. I can't remember what it is.
Oh, an 8th is
An
13
eighth
or
is
14.
13 or 14, yes.
And this leads to a wholly new and rather bizarre notion of addition and multiplication on the integers. And strangely enough, I got to it through thinking of these infinite games and the surreal numbers. This theory of adding up impartial games, due to Grundy and Sprague, says they all reduce to the game of Nim. Doesn't very much matter what it is, but it's a simple mathematical game. And then when I extended it to partisan games, I found in particular the surreal numbers. And then the definition of multiplication for surreal numbers, I went back and looked what it would tell you if you had impartial numbers, which I call nimbers now, because they all arise in the game of Nim. Well, this is the multiplication table for nimbers, and it's rather strange. And
Oh, so nimbers are different from numbers.
yes, nimbers. Here's the number. This Hackenbush game has value 3. This Hackenbush game
Has value minus.
has value -3. This one has value *3.
Which is the number 3.
Which is this, these things I missed off all the stars in front of them, which is the nimber 3. Yes, there are positive numbers, negative numbers, and nimbers which are neither positive nor negative. They're something else again, and you can actually mix them up with each other. You know, I can consider the sum of the number 3/4 and the nimber *7. That's a perfectly respectable game. I don't know if it's respectable really, but and then there are many, 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 many other things as well, many other games. Another thing that I really liked was that, you know, the theory of real numbers was sort of formalized and reduced to set theory and so on by Dedekind in the 19th century, very famous mathematician, and it was always treated as a serious part of mathematics. And here was this much bigger theory, and it just came from children's games. And I liked that. You know, we have this saying in England, or we had it when I lived there, taking the mickey out of it, you know, making fun of something. And this made fun of what hitherto had been a serious part of mathematics. It did better than the standard treatment, and it did it more frivolously at the same time. And, you know, I've had this trouble, in a way, ever since I seriously started teaching, which is that I'm interested in rather trivial things, frivolous, unimportant, you know, games, working out the day of the week, all sorts of other things. And my colleagues, you know, at Princeton or at Cambridge, as I was, I've been at each of them for about 25 years. I must be old. My colleagues would never stoop to investigating children's games. And I had to sort of struggle to get the license to be interested in trivial things. You know, I used to sit around in the common room in Cambridge, as you well know, and I now do so in the common room in Princeton. I doodle little diagrams on pieces of paper, and they are as likely as not to be about games or some other thing of the same general type as games. And at various times I have felt sort of rather out of place or guilty for studying these things, or for wasting my time on them, you know. At Cambridge I always felt bad for playing backgammon all the time. But then somehow at Cambridge I grew up into the system, and everybody knew that I played backgammon all the time, and on the other hand that I had discovered various interesting things, pieces of mathematics. And so I got the license to sort of do as I liked, and to hell with whether it's respectable or not. I remember the first series of lectures I gave in Princeton, graduate lectures, there were 4 Fields medalists in the audience, and which means, you know, pretty hotshot mathematicians. And I started off in my usual method, which is to sort of, you know, prove 1 + 1 = 2 or something, and then discuss something else, you know, very elementary, babyish stuff. And every now and then I heard a sort of snort from this front row. And so, well, I am a professional mathematician, and so I was able to sort of up the level, and I upped the level a bit. You know, I'm accustomed to lecturing in this sort of babyish fashion and nevertheless getting something done. And I can't lecture really very well in any other style. So I thought of this at the end of the term in which I gave this lecture course in Princeton. And I thought, I've got to get out of this somehow. So when we resumed, you know, after Christmas, I think it must have been, I said, these same 4 people were there in the audience, and I said, listen, you know, I'm not talking to you, I'm talking to other people. And I prefer to do it in my own very elementary way, and you may not manage to, you may not be able to stand it, so to speak. Well, they all sort of thought, oh yes, you know, we'll stay anyway. But then I determinedly did my usual babyish approach. And it took me about 10 days, but I got rid of them in the end. I mean, finally they couldn't bear it. It was so stupid and elementary. And then, you know, that's how I got the license to continue this bad habit in Princeton. And I've done so ever since, you know. They accept, you know, that it's okay for me. At least I don't know whether they do or not, to tell you the truth. It caused me some heart searching in those first few years. What actually saved me at Princeton was I got roped in by Bill Thurston, who was one of the Fields medalists I was talking about, and his former student Peter Doyle, to be a 3rd teacher in the course on geometry that they were giving. And we gave this really wonderful course, and it was wonderful mostly because of Thurston's ideas, which were very stimulating and in themselves very elementary. Before this time, I was really upset. I thought I'd sort of made the wrong decision by coming to Princeton. And then after this time, I was sort of reconciled to it. And now I behave at Princeton the way I always did at Cambridge, roughly speaking, except that backgammon is not so often played here.
I see people there playing chess.
I've never played chess, really. I mean, I learned the rules a long time ago, but I play it sometimes with my 9-year-old son, and he regularly beats me and he laughs at my moves and so on. And I get confused as to whether I'm playing black or white and things like that. I'm an absolute disaster at chess. I used to play checkers, drafts, with my first wife, my English wife, and this was really rather nice. First of all, I prefer it as a game because
It's simpler.
it's simpler. It hasn't got
Rule-wise.
these funny horse-shaped pieces and castle-shaped pieces and so on. All the pieces are very simple.
And there aren't exceptional rules for
Yeah.
if you move a pawn like this, it can be taken off.
And castling and all that sort of stuff, you know. That's what turns me off chess. It's because I don't like it that I never learned to play it very well. I have an objection to the lack of simplicity in chess. But my first wife, her uncle was a Catholic priest, and he had taught her drafts or checkers, and she regularly beat me. I won't say it was, 100-0, but it was sort of 99-1. I mean, every time I managed to win a game, it was an occasion for great celebration on my part anyway. But she had been taught one sentence by this uncle, and she said, if I tell you this one sentence, you'll
scores
beat me
will
every
reverse.
time, and I never asked her for the sentence.
You could have asked Berlekamp. Isn't that the sort of thing he'd tell you?
Yeah. Well, I would be quite interested to know what the sentence was. I could ask her, I suppose. We're on reasonably friendly terms. But she lives in England, so I don't see her very often. But I didn't want to know the sentence because it sort of rendered the game interesting to me. I picked up some books on that game fairly recently, in the last 2 or 3 years. So I've got some ideas of the kind of thing it might be.
That game is basically dead now.
Yes. I don't really know. There's this interesting guy, Marion Tinsley.
He's also dead.
Yes. Well, for ages, he was the sort of undisputed champion.
50 years.
Except that he refused to belong to whatever the federation is that governs the game and so on. And they, in turn, imposed a thing that you weren't allowed to play with Marion Tinsley. But quite often the current champion, according to the international rules or whatever, would play Marion Tinsley. And he always won, basically.
Until he played the Canadian computer.
Berlekamp knows a lot about the Marion Tinsley affair. All my comments about it really come from Berlekamp. Games interest me for the following reason. You have alternating quantifiers. I mean, I'm searching for the move, does it exist, such that for all moves of my opponent, I will have a move, in other words, there will exist a move for me, such that for all moves of my opponent, and so on. And they've got the longest strings of alternating quantifiers in the business. And I think that's why they're interesting, really. And I don't know how much you know of sort of logic and stuff, I mean formal mathematical logic, but if you take strings of quantifiers on arithmetical statements, then you classify statements as A statements if there's one universal quantifier, or E statements, and then there are AEAs, and if you ever have two together, you fuse them, If there exists a X and there also exists a Y and there was no universal in between, then you might as well say there exists a pair XY and so on. So that they're all alternating. And then there was a question that interested Hilbert and Ackermann, his student, and a few other people. What is the logical complexity of these difficult statements, and they proved results like if there are only two quantifiers in your arithmetical statement, it's decidable. But I forget which is the first one, AEA or EAE, that already includes some undecidable statements and so on. There are also results about undecidability of games. And in fact, for quite some time, there are two different sources in which game theory entered into logic. One of them is the so-called axiom of determinacy. It's a theorem for finite games. Let's say you've got a game of the type that it always ends after a finite number of moves, and when it ended, there's some little function that tells you whether it's, who won.
And in a finite game, there's always a winner.
Yes, there is. But in an infinite game, that isn't necessarily so. And there are these games due to Banach and other Polish logicians in which you name an interval in the real numbers, then I name a sub-interval of that, and let's say we impose the condition that my interval is at most half as long as yours, and we keep on imposing that condition. So we're naming a shrinking sequence of intervals, and that will converge to a point. And then if this point is in such and such a set, then you win, and if it's in the complement of that set, I win. And it's easy to see, suppose you make the set be the rationals, or it's really a partition of the reals. Suppose that's the partition between rationals and irrationals, then it's pretty obvious the irrational player wins. And it's not only pretty obvious, it's provable, because if I'm the player playing for irrationals, at my nth go, I choose an interval that doesn't contain the nth rational number. That works also if the set is not a countable union of nowhere dense sets. Banach proved that if neither the set nor its complement is a countable union of nowhere dense sets, then there isn't a winning strategy for either player. So that's how game theory first got entwined
With
with
logic.
point set theory and logic and so on. The proof of that, by the way, involves the use of the axiom of choice. So if you don't believe the axiom of choice,
You can have the axiom of determinacy.
you can have the axiom of determinacy that says every game has a winning strategy for one or other of the two players. Every game of a suitable type. And it turns out that although that negates the axiom of choice, it implies the axiom of countable choice and various other specializations. And it in fact it implies everything that you ever use in classical analysis. You don't really use the full strength of the axiom of choice, except to prove that certain nasty sets exist. You know, the first real use of it is to prove that there's a non-measurable set. Well, you know, you can perfectly well suppose the axiom of determinacy, and then every set is measurable, and analysis looks a lot nicer, you know. I mean, nobody really does it that way, but it's an alternative universe which in many ways has nicer properties than the real one, and it enables you to do all of good classical mathematics, let's say all of pre-1900 mathematics, you know, perfectly well. It's a rather nice thing. Anyway, the consistency of the axiom of determinacy is a sort of big deal. It's not provable, you know, from the other axioms of set theory. So if you adopt this axiom, you're stepping into dangerous territory, you know. You can never be quite sure that what you do is right. But that's true already.
Of choice, isn't it?
Sorry?
It's true of choice as well.
Yeah, if you, it's true of all the other axioms, you know, the consistency of any system that suffices to prove the standard things about arithmetic can't be proved without talking about a stronger system, which is really begging the question. You know, one of my most interesting 10 minutes was when I came to Princeton a long time ago, before I came here to live and so on. And this strange man, Stan Tenenbaum, offered to introduce me to Gödel.
Who he called
Sorry?
Who he called God. you
He
told-
called God, yes. There was a sort of thing, all the people interested in mathematical logic and so on, they had a whole panoply of people with sort of vaguely religious names. Gödel was known as God. Kreisel was Christ. Alonzo Church was the church. And then along came Eric Bishop, a good time later.
You were worthy enough to be taken to God.
Yes, he said, would you like to meet God, you know? And he talked like that. They all did, actually, at a certain time. And so I said yes, you know, and I was ushered into the great man's presence. Somewhere he said, we will only get to the truth of the continuum hypothesis, or the meaning of it or something, when we find the correct theory of infinitesimals.
Which you found.
Well, I thought I found, I wouldn't go so far as to say the correct, at least I wouldn't before Gödel himself. But yes, I thought I'd found the correct theory of infinitesimals.
As part of your theory of games.
Yes. And so I was particularly interested to know what his sentence meant. And he said something like, you know, did I really say that? You know? Oh, no, I don't know what I meant. Anyway, I don't think much of it now, you know, which was a bit of a disappointment to me. But still, I met the man. Stan Tenenbaum was a very curious man. He sort of dropped out of professional mathematics at the time. He kept on getting new jobs, and then at some time he'd have an argument with the chairman of the math department or the president of the university or the dean or something, and he would either be thrown out or resign in a huff, you know. And then his friends would rally round again for the nth time and write letters on his behalf and get him a new job somewhere else. This would last him another 6 months or a year and so on. And when I met him, he had become a sort of almost a street person. He used to come to Princeton, and every now and there was a waitress in this place called PJ's Pancake House, who he had done some favor to a long time ago. So she would always know when he was coming, and she would alert people. In particular, she would alert me, Stan's coming on Thursday, you know.
This was before you were in Princeton, though?
No, it's when I was in Princeton.
Okay.
So I'd meet Stan, we'd have a talk about mathematical philosophy or something. He was really knowledgeable, not only about modern mathematical philosophy, but about Aristotle and so on, you know. He would say, no, that's not in the metaphysics, it's in the prior analytics or something, you know. He referred to these, he was very familiar with all these classical works on logic and so on. And we used to have interesting discussions. And then he would stick around for a few weeks, and then he would be off to Chicago, which was where he was educated. And then he'd stick around there for a few weeks and be off to Montreal. And he just did this cycle, Princeton, Chicago, Montreal, Princeton, Chicago, Montreal. His son lived in Montreal. I can't remember whether that's the correct cyclic order or whether it was the other way around, but it doesn't very much matter. He was an absolutely fascinating character. I loved talking to Stan Tenenbaum. It reminds me of that poem, you know, the Cabots talk only to God, because Stan Tenenbaum talked to God. And he was just about the only person, as far as I could see, who talked to God in later years. You know, Gödel became increasingly eccentric, and in the end he starved himself to death after his wife died. He wouldn't trust anybody else to prepare food for him. And his wife, and then he thought there were noxious gases or something leaking out of his refrigerator. And anyway, you know, he was paranoid. And when his wife died, it was inevitable that he was going to die. He just starved himself to death. He died 6 weeks after she did. It's so strange, you know. You know, what happened to the man? Such a brilliant logician, you know. He sort of did quite a number of distinct things that nobody had done, greatest advances since essentially Aristotle. You can say something for the formalization of logic, took place in the 19th century. But Gödel actually proved some wonderful things. And that he could do all that and yet be so...
Totally insane.
Yeah, really, he was at the end of his life, absolutely insane. I talked once to Hilda Brouwer, the widow of Alfred Brouwer, who lived next door to the Gödels. And she was a big woman. And she said, every now and then she was called in to cope with Gödel, and she remembers physically carrying him upstairs, while he was sort of kicking around and so on. She wouldn't stand any nonsense. This is that. So occasionally she prepared some food for him, and he did apparently reluctantly eat it when she stood over him, sort of threatening it. That's what she said anyway. I went to Chapel Hill, North Carolina, I think it was. I saw in the common room of the math department there some typed and Xeroxed comments about Gödel and about some other things as well by Hilda Brouwer. And somebody saw me reading them, and he said, she'll be absolutely delighted to talk to you.
Was she a mathematician too?
No, she wasn't. But, she was married to one, and she was quite familiar with the species and the defects of the species and so on. So she came in and she took me around these gardens and talked to me for sort of roughly a day. She arrived about 10 or 11 in the morning, and, we parted at 7 or 8 in the evening. And she was just telling me anecdotes of, mostly about Gödel, but, about some other mathematicians. And I wish I'd had a tape recorder or something, At Durham University, there was a man called Mr. Gibby, and he was a retired professor of chemistry. And the London Maths Soc used to hold meetings, maybe it still does, I don't know, in Durham. And anyway, the thing that interested me in Mr. Gibby was a similar set of typed notes, a memoir or something you might call it, of Percy Haywood. He was the man who worked on the map colouring problem for a long part of his life. He first found, when Haywood started...
Is he the one who gave the proof?
Yes.
That stood up for a long time.
This man, Kemper, had a proof which was believed for a period of about 10 years. And then Haywood pointed out an error in it. And Haywood then proved the 5-colour theorem, that 5 colours always suffice. And he also proved bounds if you worked on other surfaces, which were later proved to be the best numbers in all but one case. In the case of the Klein bottle, Haywood's bound gives you 7 colours, but a man called Franklin
Proved that 6 is
proved that 6 was always enough. But Haywood's methods did not work for 4, although he got a lot of progress. Anyway, Mr. Gibby had met Percy Haywood, which was really quite remarkable, considering that Haywood, did his work on the map colouring problem starting in about 1870. So we had him come round and talk to the particular mathematical conference I was at. And then he also was an expert on the history of Durham the cathedral and the castle and so on. And he talked about those, which was, and gave us a guided tour of both of those places. Durham Castle is rather interesting in that it is now a residence hall. It's 1,000 years old or something, but it belongs to Durham University, and there are students who live there in this 1,000-year-old castle, which must be a rather nice thing to do.
Almost worth going to Durham.
Yeah.
Do you want to talk about a four-colour theorem a bit and computer proofs? Is that something you've got opinions on? And
Yes.
maybe even the Kepler sphere packing conjecture. You were involved with a proof of that.
The four-colour theorem was the first time that such discussions arose.
Although we'd run into it in group theory.
Haken and Appel, I almost spoonerized those two names, proved it jointly.
So they reduced the proof to an enormous calculation, which they
Yes,
did by
but
machine.
they interacted with the machine, basically. You have a part of the proof that says any map, any sufficiently large map, must contain one of these configurations, and you give an explicit list of configurations. And then for each of those configurations, you have a reducibility thing that you can colour this map if and only if you can colour a rather smaller one. And that, putting those two things together, you prove that there can't be a minimal counterexample that needs more than four colours. And what happened with the original proof is that they generated this list of configurations to be proved reducible by hand, and then the machine, they had a machine program that tested reducibility. Now, as soon as this came out, there was a tremendous amount of discussion in things like the Scientific American and the New Scientist and, in mathematics departments all over the place. And the discussion rather missed the point. The discussion was,
Can we trust
you
this?
call it a proof if the machine did it, or if it was only surveyable?
or
by
if no human could ever
Machine.
check it.
Yeah, or no human can check it and so on. Is it really a proof? The real problem was with the, let's call it the hand component, or the human component is perhaps a better word. The human component was unreliable. Even when they announced the proof, they were still finding cases that they'd missed. But what happened is, if you missed a case, you put it into the machine, and then either it proved it reducible
Or
or
it
it
found a
didn't.
counterexample.
But then, after you, suppose it didn't, then you sort of asked, well, what are the next two faces around here like? That splits it into 3 or 4 subcases, and you put those into the machine, and the machine would check that they were all reducible. Or maybe one of them wasn't, but then you do it again, and it really is. And they had accumulated a sort of familiarity with what the machine did, and they sort of knew that they were just essentially there, if whatever case you handled, it was either reducible or could be split into a few cases, which maybe one of them needed to be split a bit more, but in any case, in the end, they were all reducible. And they made the mistake, in my view, of announcing the result when, in fact, they were still finding errors, but they were eventually cleared up. The sort of public discussion of this never centered on that. The problems were not with the machine part. The problems were with the human part. The human part turned out to be highly unreliable, as anybody with any experience of mathematical proofs could have told you, There was a man whose name I think was Allaire, Allaire, who had almost finished a proof at the time that
A similar machine-based proof.
Haken and Appel published their proof, and he came up with his proof about within the next 6 months or so. And the original proof had about 2,000 cases to the tree, 1,900 and something. Allaire's proof was a bit smaller, you know. And then eventually, my colleague here, Paul Seymour at Princeton, totally mechanized the proof. He mechanized the case discussion part.
So there's no human involvement.
No human interaction at all, so to speak.
Whereas mathematicians wanted to take it the other way.
Yes, I mean, by the way, I had an idea, still have, about proving the four-color theorem, but anyway, Seymour reduced it to 640-something cases. And moreover, that has been sort of hand-checked because, hand-checked, the case discussion part has been hand-checked. The reducibility was never a problem, you know. There are several different programs have been written to check reducibility, and you couldn't run it on any one of them and it says it's reducible, you know, and they're using slightly different methods. The case that I was involved in, rather reluctantly, but I wasn't really involved, was when this, perhaps I won't mention the name.
I mean, you were involved in Hales's sphere packing conjecture.
Another mathematician claimed to have a proof of the Kepler conjecture, how densely you could pack spheres. And, well, perhaps the nicest thing to say is it wasn't a proof and the claim didn't stand up. It took quite a lot of discussion to sort of verify that.
But that was not a computer proof. I mean,
No.
computers weren't an
Now,
issue there.
Hales and his student Ferguson eventually produced a proof that the world believes. On the other hand, it started off the same kind of discussion again because it involved heavy computation. I think it was a heart attack, and I was recuperating from it in Princeton. And I heard what the Annals of Mathematics was proposing to do about this Hales proof. And I was so upset by it that I telephoned the chairman of the editorial committee and suggested I come and make a presentation to try and stop them doing this.
And what were they proposing to do?
Well, what they were proposing to do, and it's what they in the end did, and I'm still upset about it, they refereed Hales's proof, well, the Hales-Ferguson proof, which should always include Ferguson, in two separate parts. One was the sort of theoretical discussion, which they sent to a team of essentially Eastern European mathematicians, referees, who had been interested working on similar problems themselves and so on. And they issued a normal referee's report. But then the computational part, they didn't quite do that with, and it was published in another place and so on. And unfortunately, the editorial comment about this sort of left a number of people with the impression that this computational part was not thoroughly checked. Well, I mean, to say it's not checked gives you the impression that it might be wrong, you know, which I think was very misleading, because what Hales did was, in my view, set a new standard for these computer-assisted proofs. You can discover, you know, you can go to their website or something, and you can ask for when this particular part of the proof was discussed, you know, and they'll say August the 12th, 1990 something, and then you can have a complete log of all the interactions between the people and the machine on that date, and it amounted to proving a certain inequality. And suppose the inequality is for two functions of one variable. F is always less than or equal to G, Then you divide the interval up into a finite number of regions, and you check that the inequality holds at all the division points, and then you have bounds for the derivatives of the function. It not only holds, but it holds with something to spare, and it can't vary by more than so and so it's true on each subinterval. And but then it goes further than that. They carefully use interval arithmetic, so they don't just use real number things. They
avoid any round-off error.
Real numbers with possible error marks attached to them and so on. And my God, the precautions they took were absolutely fantastic. And you can examine any particular piece of it you like. And in my view, the Annals took a wrong view, which is remarkable since they're a good journal, of what the referee's job is. It's a pity, because we should be celebrating the setting of a new standard for proofs by machine.
And it probably is going to become a bigger question.
Yes, I mean...
I don't know if you were involved in any computer proofs. I mean, certainly the work on large sporadic groups involved a lot of computation.
Yes.
I don't know if J4 was computer dependent.
Yes, J4 was an example. I was, in a way, involved in J4. Didn't do any programming or anything, but...
you were one of the authors of a paper.
It was a fairly big computation. However, I don't think any, in that case, or in any of the similar cases that, involve these big groups, that there is really any of this sort of supposed difficulty involving the machine.
Well, no one caused any problem in group theory.
It was clear what the machine was doing in every case, I think, and it was doing things where you could reasonably expect that it was getting them right, They were sort of... After all, suppose in a mathematical paper, somebody has occasion to refer to the product of two 5-digit numbers, and nobody feels, I have to get out my calculating machine or my thing and check that the product of these two 5-digit integers is the other one.
But was the use of a computer for either the four-color theorem or the Kepler conjecture very different from that? The machine was doing fairly straightforward calculations.
Yes, that's what I think. In all these group theoretical things, with many of them, the essential part was a coset enumeration program.
Or a multiplication of matrices.
And that's routine. And if you don't believe the answer to so-and-so's enumeration, you can do it on somebody else's program.
But you're still left with a machine doing it at the end.
Yes, you certainly are. I feel a little bit unhappy about some of those things. I suppose, since I've gone on about the monster, I'm unhappy with the computations involved there, even though, in my version of Grice's construction, and I think in Grice's original construction...
His version, he said, the computation was so large he had to do it by hand instead of by machine,
that's
was
right.
his quote.
Yes, that's true. When I've had various plans for studying the monster, and a lot of them, you will remember Len Soicher, a mutual friend, he proved a lot of things about the monster by coset enumerations, but the final things, to get to the monster itself,
was beyond
it was too big to be done by machine. It still is, I think. The big thing there was, to find clever ways of thinking of it by hand. Grice found a way of constructing it with no use of computation, I think. There may have been some trivial use, I don't know. I simplified his construction. You know, I read his paper to see what to do.
And he gave you a roadmap for your
Yeah.
construction.
And then I had this idea of using, well, Parker had the idea. Parker had this clever construction in terms of a loop, which there were two things wrong with it. First of all, he didn't feel competent to actually do it himself. And then the other thing is, he had the construction slightly wrong. You needed to do an extra twist. But, and, you know, he didn't find that twist, and I did. This was on the occasion when I was sitting outside while my wife was attending the lectures. It produced a very simple construction, in my view. Yeah, well, you know, when you talk about the monster, it has a terrible effect on me. I want to start thinking about it again, you know.